I'm happy to present to you today our facility at Charles University, the near ambient pressure X-ray photoelectron spectroscopy. My talk is named Present and New Frontiers in Materials Research by Near Ambient Pressure XPS. My name is Smid. I'm from Charles University, from the Nanomaterials group at Department of Surface and Plasma Science. And my colleague, Dr. Mikhailo Vorochta, gave a talk on basics of near ambient pressure XPS yesterday. So this is the continuation of this course, which should be more focused on practical use of this equipment. And I will try to describe you in detail our apparatus here we have in our department and the results that we achieved. After this talk, which will take, let's say, about 50 minutes or so, but we can stop by any time. We'll move to the laboratory where my colleague, Dr. Vorochta, will help me to conduct an experiment. So my talk will very first shortly, because I don't know your background, so I will introduce a little Charles University as part of CERIC, the Central European Research Infrastructure Consortium. I'll talk shortly about CERIC as well, because you already heard about the theoretical point of view of near ambient pressure XPS. I will just very polish a few critical points. And then I will show you the setup in a 3D model before we finally move to the lab. I will also talk about the achievements with the other users, the other groups, because it's based on international open access experiments, and tell you about our plans for the future as well. And finally, as I already mentioned, we will conduct experiments with you, which we chose with my colleague, the CO adsorption on palladium single crystal with a surface orientation 110 in the near ambient pressure cell. So you can get kind of a touch, at least in this kind of way, to the equipment. Charles University, where I am appointed right now, is very old university. It was established by Charles IV, the Roman Emperor and Czech King, in 1348. Nowadays, it has more than 46,000 students. It has 17 faculties. One of them is Faculty of Mathematics and Physics. And it's member of the European University Alliance, together with Heidelberg University, Sorbonne University, and University of Warsaw. CERIC, as you probably know, is a Central European Research Infrastructure Consortium that put together institutions with cutting-edge equipment from 8 or 9 countries within mainly Central Europe. One of them is a Surface Physics Laboratory Material Science Beamline, SPL-MSB, which is the Material Science Beamline is built and fully owned by Charles University nowadays. It's a single-sided operation of large research infrastructures, and it is a partner of the laboratory in CERIC. This consortium was established in 2014, and up to date, we are actually offering from our side, from Charles University, 4 or actually 5 different equipments. Besides the near ambient pressure XPS, which we fully supported, we also supported the XPS, X-ray spectroscopy, X-ray photoelectron diffraction, field emission secondary scanning electron microscope, and also from the Italian side, the material science beamline. And since the end of this year, from autumn, we'll be also offering Enviro-SK, which is also XPS for as a user support. How does near ambient pressure HPS stand within those equipment? You can see from those numbers, as you see the number of proposals that were actually filed within the last 4 years is increasing with each year. The 2020 data are a little bit bended by the situation about coronavirus, so I'm not showing them here. And the number of actually allocated experiments, which mean that are actually conducted, you can see here's also quite a big number for the near ambient pressure XPS. So it's a very popular technique among the scientists from all around the world. And we hope it will stay like that in the future as well. I mentioned it's international, which means that in fact, anybody, anyone in the whole world from any group can write a proposal, experimental plan, bring ideas, and me and my colleague, Dr. Michal Vorokta, are checking those proposals from the technical viewpoint. And then the next level is a scientific evaluation. After that, the proposals are either awarded or not by the financial support. And it means it's a travel support and also accommodation in Prague. Those scientists can come here and conduct experiments with our support here. You can see we have the users from all around the world, mainly from Europe, of course. We have, for example, Institut Charles Gerhard Montpellier from France, RC Lyon, the famous institute for research on catalysis and environmental and the environment, University of Pierre Marie Curie, our European Synchrotron Radiation Facility. We also have users from United States. It's Professor Ernst Bauer from Arizona State University, or users from Kyushu University in Japan. I didn't show in the map the users from Czech institutions because there would be probably no space. So you probably heard a little, or quite in detail, honestly, from Misha, from Mikhail Vorokta yesterday about the basics for XPS. So I'm skipping the basics of the X-ray photoresin spectroscopy and pick up those kind of like a critical or crucial points that are crucial for the near ambient pressure. The early stage of development was that you had a small pressurized cell within an ultra-high vacuum chamber with two orifices, one for the X-ray coming in, interacting with the surface, and the photoelectrons coming out by another orifice. The next stage was that you had actually the whole chamber was in high pressure. There was a special window for the X-ray coming in, and you brought the analyzer within this optics closer to the sample. So photoelectrons are actually escaping the surface surrounded by the gas can escape. And of course, after several interactions with the gas molecules that are around them, the electrons can freely move to the analyzer through the optics. Another stage in development was that you have actually a high pressure cell within the ultra-high vacuum chamber. We are bringing gas in and out. Of course, you have to have another window that protects the high pressure from the vacuum here, because typical pressure at nowadays near ambient pressure equipments, lab-based sources, and also wide synchrotrons are usually around a couple of units of millibars. The cell itself can be pressurized up to 50 millibars. However, the measurement might be quite complicated at such high pressure because most of the gas or most of the signal is attenuated. Another is in the picture D here is also kind of a high pressure cell that is connected to the optics of the hemispheric analyzer. It's intentionally removable, and its advantage is that the its volume is much smaller than in this picture. This, in this case, kind of a backfilling setup. And in this case, when you have some corrosive or reactive gases, that might be a problem for some other parts of the chamber. In the beginning, there was the photoelectrons coming from the samples were not focused, so most of them were lost on the way to the analyzer. The modern system nowadays have optics with electrostatic lenses that are actually focusing the photoelectrons beams within each stage. And so the signal is kind of, you are actually capturing almost 100% photoelectrons coming out of the sample, also because of the shape of the cone. We call it nozzle. I will show you how it looks like in reality. And our system is also 3 stages, and you are actually drastically reducing the pressure. Already in the first stage, the pressure difference is about 5 order of magnitude. Then it means if you are 1 millibar here, you are on -5 millibars, -7, -9. And already in this stage, the inelastic mean free pass of photoelectrons is ineligible. You probably saw those pictures yesterday as well. So I just very shortly remind you the trick why we are actually able to measure at higher pressures is that you have a very small aperture in the nozzle that is brought close to the sample. Typical, the distance is in hundreds of micrometers. We are using 300 micrometers, 0.3 millimeters. Nowadays, the systems, or there are already experiments of systems that are operating at the real ambient pressure. In this case, you have to very small aperture, bringing to very close surface. And of course, this brings a lot of technical problems. There is an example of so-called Beer-Lambert law. Based on that, you can actually calculate the signal attenuation based on the surrounded gas. So if you have, for example, measurement in 1 millibar of oxygen, where the electron free pass is about 4 millimeters, and you measured your photoelectron escaping from the surface coming to the optics of the analyzer is about 500 electron volts. So you are losing about 26% of the signal. Another loss is because you have to use a special windows to kind of seal your high pressure cell and protect the ultra high vacuum around. So the modern system are using silicon nitride, Si3 and 4 windows. And this is also still covered with aluminum foil to make it more solid. And you can see that there are about 2 absorbance edges because of the materials used. The silicon is about 100 electron volts, nitrogen about 400. However, because we are using lab-based source, X-ray source, which has energy around 1486 electron volts, so most of the light is actually go through. So it's almost 100% transparent for the source we are using, including the aluminum foil covered. This was quite, oh yeah. In this graph, there is so how popular it is to use the near ambient pressure. As you may know, Kai Ziegbahn got Nobel Prize for the development of X-ray photoresistance spectroscopy. He got a Nobel Prize in 1981. It's based on the photoelectron effect, from the photo effect that was actually described by Albert Einstein, who got a Nobel Prize for it in 1921. So you see, it's quite interesting technique. It's very surface sensitive. And already in 70s, 80s, or the last century, Kai Ziegbahn was kind of experimenting with high pressure cells. It's in that time mainly with liquids, because it's very interesting area of using XPS. However, the real breakthrough was around 90s, last century, or the beginning of 21st century, with bringing synchrotron lights in it, especially in ALS in Berkeley or Bessie in Germany. And this is a cumulative number of papers that are actually dealing with the near ambient pressure. This is kind of estimation, because not every paper dealing with this technique are actually using this NAPXPS or APXPS, ambient pressure XPS, in the keyword. So, but let's say it's more or less correct. You can see this is kind of, those are the system installed within the past years. In the beginning, or around the beginning of this century, it was mainly synchrotron-based systems that were leading this scientific field. But recently, in the past 10 years, the lab-based X-ray sources are taking over. The reason is very simple. Not everyone has a synchrotron ring behind their university campus, and to just rebuild or buy already built system of this near ambient pressure using lab-based X-ray source is much easier and cheaper. So you can see that it just goes quite nicely, and that's those red, which is lab-based, are in leading. Prague is here. Our system was installed in the end of 2015. The graph in this one is the same. It's just showing using near ambient pressure in different fields. In the beginning, as I already mentioned, the most focus one on the liquids, and it's kind of like getting in front in the past decade, and the same is for the electrocatalysis. The system in Prague looks like this on the 3D model that Specs sent us. The near ambient pressure XPS part is just this one here, is this near ambient pressure cell. This is all together. It's a combination of different ultra high vacuum chambers, which me and my colleague will show you in detail within like 1 hour for sure. Here is the hemispheric analyzer. Those are the optics. This is the entrance of the analyzer with those electrostatic lenses. Here is the first pumping stage, second and third. Each of them are pumped by the turbomolecular pumps, pre-pumped by the scroll pumps. On this stage, we have installed the quadruple mass spectrometer. Here's a load lock where you put a sample for the very first time before you start the measurement. Its volume is quite small, so it's very easy and fast to pump it out. Then we have unnormally long transfer chamber. It's because that time as this machine was installed, we were already counting, or our boss was counting on the installation of on another near ambient pressure machine. We have here buffer chamber with electrochemical cell, and there is also low energy electron diffraction for checking the surface, and we have UV lamp. This X-ray source have in this part the monochromator that makes the data more resolved, better resolved with a better signal. We have charge neutralization flood gun because sometimes your sample is not conductive, and it might be the same problem as you might meet during the measurement, during the observation by scanning at a microscope, when you have a charging of those electrons on the surface that make the image unclear, blurred, and unfocused. So we have something similar. If the sample, even though it's grounded, it's if it's not conductive, it might be a problem. The near ambient pressure cell can actually solve this problem partially because at higher pressure and elevated temperatures, the charging problem is partly resolved. So as I mentioned, we have quadruple mass spectrometer here, ion spatter gun for cleaning the samples. We have a couple of operators for operating clean metals. There's a video camera, because when you are approaching your sample close to the nozzle, to this kind of like entrance to the analyzer, you have to be sure you are at the right position and you are not going to hit the sample. So this visualization is quite important during the measurement, and you will see it in the real soon. We have a couple of gases. We have pipelines. We can combine those gases together. There are 3 flow controllers from one side. We have also another 2 lines going in for operating the vapors from liquids like water, ethanol, methanol, and others. We are also experimenting with ammonia, even though this is not the ideal gas used in ultra-high vacuum chambers. It's corrosive, but in a small amount or with a mixture with other neutral gases, it can actually work. And we did some experiments with ammonia as well successfully. So there are few manipulator. One is actually bringing the sample from preparation chamber to analysis chamber, where we can, through so-called wobble sticks, take them and move it where we need. We can heat up the sample from around, let's say, room temperature, cool down a little, let's say 260 kelvins, up to 1100 Kelvin. And with a specific sample holder that have actually a hole in it, you can heat up the sample directly by the thermo emission. And in NAP manipulator, which is actually within the cell, we can heat up the sample to 900 approximately Kelvins. Also, this stage can be cool at certain setup. As I mentioned, we have near ambient pressure SPM scanning probe microscope that put together STM scanning tunnel microscope and AFM atomic force microscope. This is quite interesting combination when Specs installed this SPM together with our XPS, both near ambient pressure. They told us it's about 5 of such combination together in the whole world, and this was the only one in Europe. Probably there was none in the United States at the time, and there was a couple of them in Asia. So the reason is that it's quite tricky if you combine those techniques together. STM is very sensitive for vibration. Now imagine you have a lot of systems working around pumping. So it's tricky, and we have to always kind of manage our measurement. But so far, it worked. This is the cell that is actually installed in this part here under the transfer chamber. You can see it here. There's some such table. This cell is retractable, so we can actually bring it closer to the optics of the analyzer and retract it. You can see here this kind of black part. This is this ring, this O-ring that seal and kind of help to keep the high pressure inside the cell. Here are doors that can be opened, sample moved in and closed, and cell bring to the analyzer and start the measurement. How it looks if in a cut, you can see here there's a heating system, there's a heating filament that actually heal the backstage of the stage where the sample is connected. The volume of such cell we have here in Prague is about 0.4 liters, and the nozzle aperture is 300 micrometers. Here's another drawing. So your sample is here. This is the heating system. You can also cool it with liquid nitrogen. There are a couple of windows all around that actually allow the X-ray source, X-ray light, come in the sample and interact with the sample, allow the photoelectrons to escape and be captured by the analyzer. We have another window for the camera. There's also a window for the UV light, because we can also measure the valence band by ultraviolet lamp that is also installed on the sample I mentioned. Here are the several pumping systems that are actually decreasing the pressure and allow the photoelectrons coming through and reach the detector. This is the recent setup we have, and I will show you soon. So here is the little load lock, a small chamber with small volume that you put a sample in. Here are the doors. And we started our experiment already with the sample in. It will be cleaned. So we started with putting it inside the near ambient pressure cell and conduct the experiment with the pressurized carbon monoxide about pressure 1 millibar. Before that, we measured the sample in the vacuum for comparison and to see what changes or what adsorbate we actually achieved by this experiment. That was about the machine before we go to the laboratory. And I will shortly talk you or tell you about the experiment achieved by the users within the CERIC. So the scientists were actually in prison here. The last 1.5 years, we are doing the experiments that we receive the samples by mail, and we conduct the experiments here, and we talk with the scientists via either Zoom, Skype, or other like MS Team, and discuss what should be measured and how. The usage of our equipment is quite broad. We have examples from electronics, mainly catalysis, electrochemistry, gas sensing, and even biological interfaces, and of course the fuel cell materials. First example was published in Advanced Materials, and it deals with interesting material. It's lanthanum aluminum oxide on STO, strontium titanium oxide. This is quite interesting material, and it's known mainly for the electronic transfer, because if electronic transfer, it's quite simple. It's just electrons transferring from one element to the other one. That can be easily captured by the XPS. It's changing the binding energy. New chemical states can be observed. However, it was observed that also the ionic charge was actually occurring on the surface. It's quite interesting. And this is broad work combined the near ambient pressure in our facility together with the near ambient pressure at synchrotron facility. And the goal was to understand the nature of charge transfer of on oxides interfaces or heterostructures. And it was found that the ionic charge transfer plays a crucial role and can actually influence the electron charge transfer as well. So the strontium atoms that are actually under the subsurface were actually observed to be on the surface with specific reaction conditions when the material is surrounded by a specific gas, in this case of it's oxygen. So you can see that actually after the introducing the gas inside the chamber, so you can observe a new species. So this was kind of proof together with other techniques that this is actually really happening, that you, based on the surrounded gas, the strontium atoms are traveling through the topmost layers of this lanthanum aluminum oxide and are trapped on the surface. If you get off the oxygen, so the effect is actually opposite. It was also on the cover page of Advanced Materials, so it was quite nice work of the German group. Another example is from a French group from Ars Lyon. They are also it's example from the catalysis. It is known for quite a long time that cerium oxide has special properties. It has this kind of switch. It can easily switch from 3+ to 4+. So it means you can either, the cerium oxide as a material can either accept or release oxygen, which is quite unique property, especially in catalysis. And together with the platinum, it is very good catalyst. You will see soon that a lot of groups is actually using platinum. So this combination is very interesting. And it was not known what is actually responsible for the CO oxidation that works so perfectly. The oxygen comes from the stereo support or from the platinum oxide that actually is creating or around the platinum islands on the surface. So this group brought a powder sample. We mounted it in a mesh, in a metal mesh, and spot welded it on the surface. So we are dealing with different kind of materials, and you always have to think and come up with some good way how to mount the sample for the measurement. And we introduce the oxygen in the sample. Here are photoelectron spectra from the surface, from the platinum. It's actually core-level spectra of platinum 4F. And you can see that besides the platinum, metallic platinum, PT0, there are two other platinum oxides, PT2+, which is PTO, and PT4+, PTO2. Those are the two stable oxides of platinum. And in the oxygen, there you can see there's a combination. If you put CO in it, so you have the reaction gas of oxygen and carbon monoxide. This reaction gas leads to the production of CO2. You can see that the platinum 4+ is decreasing, and on the other way, the platinum metallic is increasing. However, the contribution of PT2+ is unchanged. If you switch off the oxygen, so you close the oxygen inlet and you let just carbon monoxide being in the chamber, the sample fully reduced to metallic platinum, which is not surprising because CO is reducing molecule as well as hydrogen. However, if you put oxygen back, the sample is almost fully oxidized. So it can actually, it shows that the sample is history dependent. Before the reaction conditions, before the reactions, what the gas was there before, it can actually influence the behavior. So this group, together with a combination of other technique, including NEXAS, the near-edge absorption fine spectroscopy, they actually find out that the PTO is quite important and is crucial for the CO oxidation in this kind of type of catalyst, the platinum on cerium dioxide, or CO or cerium oxide. Another group is also dealing with catalysis, but not for the CO oxidation, but for ammonia oxidation. The material that works for this purpose was the platinum titanium dioxide. Again, it was a powder that was pressed in the metal mesh and spot welded on the surface. They prepared several samples with different techniques. I pick up for the example the impregnated powder that was, as it is, received and then reduced. So this is kind of like this IMP is impregnated and H means it's impregnated powder, impregnated sample reduced. You can see that as received, there are also again a combination of metal platinum and those two oxides, PT2 plus and PT4 plus. However, after reducing, the PT4 plus PTO2 completely changed to metal platinum and platinum PTO. If you put those materials in the reaction conditions, so it means a combination of ammonia and oxygen in the ratio of 42, or actually 1 to 40, the total pressure of 1.4 millibar, they behave completely different. And also, again, usually the groups that came to our facility are already characterizing their samples by different techniques. So based on other techniques together with the techniques or with our experiment, they can conclude that actually, again, the sample, the hydrogen one, the reduced one really actually works for the ammonia oxidation. As I mentioned, we have quadruple mass spectrometer in the first stage, right behind the nozzle. So all the products that are actually creating on the surface of the sample are going through the aperture and are analyzed in the first stage by the quadruple mass spectrometer. Here's a comparison of such mass spectrometer data, and you can see that 17 is actually the mass for the ammonia, because nitrogen has a mass 14 and 3 hydrogens, each one is 14 plus 3, 17. And the product, which is N2O 44, is actually increasing even below 100 degrees C. And other products like water, nitrogen, you can all see them here. This is comparing with the blank experiment without a sample, where you can see that the production of N2O is actually quite above 200 degrees C. That, of course, sometimes also the stage is reacting, so we have to be sure that whatever we are observing is actually coming from the sample. And you can see those products also on the photoelectron spectra. Another example is from gas sensing. That's quite also a nice field of science, and it can perfectly fit the purpose of near ambient pressure XPS, because the sensors are changing their property, mainly the resistance, and it's changed the resistance based on the surrounded gas. As you can see here, for example, this is probably work that Dr. Borokta was talking about yesterday, so I will easily skip you. Just technically, I will tell you, we have two thermocouples inside the high pressure cell. One is measuring the temperature of the stage, and the second one is measuring the temperature of the sample. We usually connect this thermocouple very close to the sample, either by spot welding or putting it under some metal that is screwed to the sample holder. For those kind of gas sensing experiments, we are using this sample thermocouple as a measurement for the resistance. So we control the high temperature only by the stage. Already it is calibrated before. Another example is again from the catalysis. It's about the liquid metals, which in this case is bismuth, and with together combined with iron catalyst, it could be used for the so-called light olefin synthesis using the Fischer-Tropsch reaction. And again, combination with other techniques, it was shown that the bismuth migration during the activation of the iron catalyst is actually creating so-called core shell structure, where the bismuth is either sintering together or is covering the iron catalysts, which is grown or prepared on carbon nanotubes. I will not go to the detail because it might not be so much interested for you. The same other example for the catalysis is also bismuth modified catalyst, but for oxidative dehydrogenation of ethane. And just to show you how different samples can be prepared and measured, so this group brought a sample that was in a small shape of like a ball. It's in about 4 millimeters in diameter, and you can either crash this sample, make a powder, then press it in the foil, or like in this case, there is a hole in a mesh, and the mesh is then spot welded on the surface. So this kind of like a surface was measured for the experiment. So it's all connected, it's conductive, and you can also measure this kind of not typical samples. Now we move to a little bit higher level of measurement, because we used to have, now we are working on different design, hydrochemical cell. The electrochemistry is quite interesting field of science, and before, or mainly, it is like self-standing. Usually you don't have combination of hydrochemistry and surface science, kind of ultra high vacuum science technique, because you are using electrolytes that are usually acidic, and this is not the perfect material to be used in ultra high vacuum chambers where you want to keep it very clean. But we conducted such experiment, and again, this was very huge work. You can see how many people was actually participating. It combines a work from the synchrotron, from the material science beamline in Elettra, in Trieste, Italy. It's combined the work from German group from University of Jülich. So, and partly, of course, from our department, where you really have glass hydrochemical cell. You can conduct the hydrochemical experiments, measure the linear C voltammetry, cyclic voltammetry, and this is actually connecting the sample, because you are taking the sample from the vacuum and you need to connect it to get in contact with liquid. So you have to fill it with some inert gas before you are actually taking the sample in. So that's how it was done. And this particular paper is actually kind of dealing with the problem of so-called materials gap, because in heterogeneous catalysis, most of our current fundamental knowledge originates from surface science studies on single crystals. But they are too simple from the real materials. So to kind of bridge this so-called materials gap, this group prepared on single crystal, which is the kind of model system. They prepared small islands of platinum, and kind of mimicking the little bit real system, so kind of bridging those two different worlds, the real one that can be used in electrochemistry, and the one that is actually the pretty much model that is suitable for ultra high vacuum. The critical questions those authors asked was if the model catalyst preserved their atomic surface structure after entering the electrolyte system. The answer is yes. You can see the prepared sample under ultra high vacuum conditions, checked by the low energy electron diffraction lead, AFM, XPS, and then putting it to the liquid electrolyte, really do the cyclic voltammetry measurement, and then bring the sample out the liquid, clean it with pure water, let it dry, transfer back. you can see that the support, the cobalt oxide, CO304 single crystal on iridium 100 is actually unchanged. Together with the platinum, there is a little more platinum dioxide created. Otherwise, you can see the metal and the kind of oxide remains the same. So it was actually shown that the site occupation of adsorbed CO changes dramatically for platinum aggregates, and the electronic metal support interactions in this system led to the formation of oxidized platinum species on the metal support interface. And this oxidized platinum species can actually be readily reduced and renewed. And this can open the new synergistic reaction pathway involved both metallic and oxidized platinum at the boundary. That was just quite few examples from what was done mainly from the recent 2 years. And I mentioned at the beginning of my talk that the Enviro SC is another abbreviation for X-ray photoresin spectroscopy. It stands for electron spectroscopy for chemical analysis. And SPECS is actually creating so-called Enviro SC that will be suitable for measuring biological samples and other samples that are difficult to be measured by conventional NAPXPS, or when you need the measurement to be done under higher pressure. So this will be installed in our institute within a few months, and we will be welcoming new users to actually use this new device. I also mentioned about the future development. A couple of years ago, I was in a conference that was it was a small conference in Barcelona, and the main topic was cerium dioxide. However, 90% of the talk were actually about the operando technique using to studying this material. So that was actually showing the trend that using the conventional NAPXPS and study the model system, which are very well defined, it's nice for the basic science. But if you really want to understand the little bit more real system, you need to go to higher pressures, study them at operando conditions, at the conditions or reactions that are actually operating in the real. So our boss bought another cell, the very same one, which will be rebuilt for fuel cell studying. That, as you may know, the fuel cell is a device that actually convert the chemical energy directly to the electrical one. You have hydrogen and oxygen as a feed, and electrical as the kind of like a result, and the only output supposed to be the pure water. So you have different electrodes here, anode and cathode, and to study what was actually happening on the cathode side, that is very crucial for the reaction. So we are building a machine that brings the hydrogen, feed through the stage, feed the fuel cell setup built inside in this side, and from the other side, which is actually the inner part of the high pressure cell, will be filled with oxygen. So you can actually see the real changes under operando conditions when the fuel cell is operating. So you can heat the stage at the desired temperature, which this proton exchange membrane fuel cell usually works at 80 degrees C, and you can also measure the electrical current as a kind of like a result of its operation. This slide is very shortly about telling you that in science there is no age limitation. Professor S. Bauer is the one I mentioned in the beginning, the Professor Emeritus at the Arizona State University. He was also several times in our institution to give a talk and also do the conduct experiment within CERIC. And he was the one who actually gave us a lot of ideas and kind of tips for improvement. This is the good thing about this work. You are dealing with different people, different scientists from different background. Each of them bring new ideas. They can help you to understand your own machine, and you can help them to get some good data. So this kind of cooperation is very fruitful for all sides. So this is from my side, everything I want to start with. And I would like to thank you very much for your attention. If you have time in the future or even now, you can actually check those web pages. On this web page, there's a 3D view from our laboratory, so you can actually imagine you are standing there and you can move your mouse and you can see different view angles of our equipment. And I would like to thank you again, finish this introduction, give the word to my colleague, Mikhail Vorokta, who is already in the lab, and I will be there in a couple of minutes to joining him, and we will do the real practical session on the equipment with your help. Thank you very much.
Okay, guys, thank you, Brett, for a nice introduction. So I will take maybe the attention to myself now. So I am now in the NAPXPS laboratory. I hope you all can see me because, you know.
Yeah, I can actually see you, so I believe the other as well.
Mainly you, so maybe you should switch off your microphone and your camera, and then maybe yes, the system will switch to myself. I don't know.
Perfect. So thanks for your help, and I'll see you soon.
Yeah. So Brett will come in some minutes because we have laboratory in a bit different building. So this laboratory is quite new, so there was no enough space to build it directly in our department. So we built it in a bit different place. So anyway, I mean, I think today, as Brett told you, we should try to do some simple experiment, which I think will show you how to perform such kind of experiment, how to operate maybe this equipment. So actually, I guess this session will be something similar to what we recently do with users, because as you know, because of this pandemic, users cannot come to the lab. However, they all quite frequently send us samples, and then we just actually using Zoom, we communicate and we try to do experiments. So together, of course, with users, we a lot have some our own experiments with our students, with other colleagues which work in our department. So you saw some examples from me and yesterday, and from Brett's presentation today. So in this laboratory work, I guess we will use maybe two computers. One is this one, which is actually the computer which we use for data processing. So it means we have here installed some softwares which can be used for fitting spectra, for some data processing. And there is another computer here which is actually measurement computer. For that one is used for measuring. We do not do any processing of data there because it slows down the computer, so it is might cause some problems when you do measurement. So I will, or we with Brett, after he comes, we will switch sometimes from one computer to another computer. Just one computer is called NAPXPS Lab. This is this one. Another is called NAPXPS Lab 2. So I guess you will. It will be convenient for you. Okay. So at the moment, the equipment is behind. We can show you maybe some video of it, but I guess it is better if you try to look it from those 3D picture which Brett just just advertised several minutes ago. It can be also found on our web page, so I can send you the direct link. You can click on it and then make some some like excursion, yeah, to look it. But anyway, you saw how it looks, from those many pictures we saw. So the important things is that now we have a sample inside. We will use palladium, just single crystal, which is known catalyst for some like CO catalysis and so on. We clean that crystal by sputtering, and by annealing. And what we would like to do next, it will be just to transfer this sample to the NAP cell. So we will try to show it somehow using camera, how it works normally, how you approach with the cell, because I told you yesterday that you can do two types of experiment. One is like in UHV, it is mostly when you do some UHV study or like model studies and so on. Another one, if you want to do NAPXPS, you need to bring this NAP cell to the analysis chamber, to lock it to analyzer, and then to insert the sample. And then after we put the sample in, I guess we will switch to another computer, and I think we'll start like measurements. Start X-ray source, dose some gas, maybe CO and oxygen. We can try to heat the sample to see there is a production of CO2. So because palladium, as I said, is a catalyst for, good for CO oxidation. Also, we will do some NAPXPS measurements, so to see if we have some adsorbates on the surface, like CO, oxygen, gas phase peaks from both gases. The adsorbed species. Also, we check the palladium oxidation state because of adsorption, it should start to oxidize a bit. So there should be some additional peaks appearing. And depending on temperature, it should have some evolution. So all these, I guess, will be quite like simple, but I think quite evident. For you to understand how normally the experiment is done. Yeah. So if you have some questions, you can always interrupt us. Just switch on your microphone and then just ask what you need. And we will answer. One problem is that here we have like many pumps, so the noise is here a bit higher than the average noise. Normally in the lab, but I hope this Zoom, it has some special like attenuation of the noise, so you can hear me and that like without problems. However, if there will be some problems, we can try to switch some maybe pumps. It is possible to do for some shorter time. But the best would be if we just leave it as it is. Okay, so Brett is here.
Yeah, so
I see that somebody switched.
Okay. I think we can just keep one video on, and I forgot totally to ask you guys if you have any question in the end of the talk. You can even ask now if you still remember. If not, you can interrupt us anytime.
Sometimes you can also write something to the chat, because some people maybe they are not very confident to ask something, as they maybe are not, they don't know us or so on, but they can type it to the chat and we will check from time to time the chat and then answer your questions. So just feel free. These practical sessions should be kind of interaction with us, and this is an opportunity for you to ask something. Maybe in future some of you will try to do such measurements. So yeah. So like this. Okay. So let's start. Maybe first things. Maybe let's switch to second computer, because in order to insert the sample to the NAP cell, we should first to send. To move with many manipulators, and it is all controlled by computer. We have a software which operates all those manipulators. There is one. This toll manipulator, which is we call it UHV manipulator. So it moves sample from preparation chamber down to analysis chamber. then you should take the sample from this UHV manipulator and move it again up to leave the space for NAPXPS to come.
Mikhailo, please, one question. So my name is Rada. I'm from Belgrade. Do you, oh, there is some microphonia, I think. So when you put the sample in, you can load only one sample at a time, or you can load several samples to the load chamber?
I mean, to load log chamber, we can load many samples, but for NAPXPS, we can load only one sample.
Yes, yes, I know that. But I mean, when you put one by one, but you can store them in the load log chamber.
Yeah. Actually, Brad here now has a notebook, so he can, move it and maybe can show you. We have one small storage chamber with a parking, so we can load there up to 10 samples to keep them in vacuum. For example, also if you do some study in an upcell, then you can take the sample out and not like expose it to air or something. You can store it in this parking. This is possible.
And you have some limitations on the size of the sample. I mean, physical.
Usually we use a standard like holder. This is specs from specs. It has size like 1.5 centimeters by 1.5. However, you need to keep some space for. I mean, when you insert the samples, there are some plates. So it means that the sample should be not higher than 1 square centimeter. It can be piece or it can be 1 by 1. But this is the maximum size.
Okay, 1 by 1. Okay, thank you.
I mean, if it's powder, usually you can we take some foil or we take some mesh, metallic mesh, which is inert, and we press this powder in, and then we somehow fix it to this sample holder.
No, what we have are the films. And the films usually have one part that is not covered, like the silicon oxide substrate, and we have the film, but one part is probably bare, but it can be small. Well, actually, we have substrates that we can cut to our requirements. So 1 by 1 is fine.
One by one, but maybe even smaller is possible. I mean, the smallest size, I guess, is 2 by 2 millimeters, because the beam size is like below 1 millimeter, but it is usually good to have some a bit bigger sample in order to fix it somehow, you know. Just to fix it, you need to use some plates, or maybe we sometimes use wires, and we spot weld these wires to directly to sample holder, so it is somehow fixed by this way. So 2 by 2 millimeters is, I guess, the smallest size, and 1 by 1 is the highest, is the biggest.
Thank you. Thank you.
So just to technically show you, here's a sample holder we usually use. It's a standard from specs. You can see those 4 holes that can actually be screwed like a piece of metal with holes as well, and you can put a sample on that. Or as Misha mentioned, if the sample has not standard size, we can actually use the kind of stainless steel foil, cut stripes, desired shape and size, and spot very directly on the stainless steel
on the stage.
And there was not a sample in the past 5 years that we will not be able to deal with. Sometimes it takes us half a day to really mount the sample on the holder. It's not usual, but sometimes it does. But then, you know, if we have like 4 days experiment in a row with the same sample, that's actually good. So it's a well spent time, and we can be sure that everything is perfect. So if you put a sample in the chamber and there is not good contact with thermocouple, we have to take it out, do it again, and to really be sure that the sample is very well prepared. So it takes time, but it's important.
And then when you transfer from the NAPS chamber to the STM part, AFM part, it stays on the same holder?
Good question. Good question. It actually, that's not how to say this word. That's not compatible, because the STM part, it's also high. It's also near ambient pressure, but it has to be special double-decker. So a double-decker holder, because you put a sample upside down and you bring the tip close to it from the bottom. And the size is the same. However, our colleague has two those sample holders connected with the distance kind of piece of metal spacers, and there is a hole, and he put a sample in, and he's just
so actually we were quite surprised, because when they were buying this STM machine, and it was like 2 or 3 years later after NAPXPS, so we expected that everything will be compatible. And then after it was built, we realized that actually it is not.
Okay.
We study the same sample in NAPXPS and then transfer it to STM. I mean, usually if we want to do same kind of experiments, we use the same crystals. I mean, however, one is mounted on double decker, one is mounted on like NAP holder.
And you just transfer them separately to other, okay, to do modules. They are independently measured. Okay, I see.
Or we can
Thank you.
use the same chamber, analysis chamber for preparation. So we can prepare thin film by deposition in analysis chamber for NAPX and the same film for STM, and then we combine the results. However, it is not the same sample.
Okay.
And honestly, also the temperature is not the same. You need to calibrate those two different temperatures on different holders. We have experience, it's actually not the same. So the best way how to overcome this problem would be if you can prepare your sample under ultra-high vacuum conditions, and we are capable to use one of those operators to prepare the sample on the double decker that can be used for the near ambient pressure STM, and then you can use such sample holder for the actual near ambient pressure XPS.
So the opposite way.
Yeah, but there will be a problem, as it is double decker and sample is on second floor, so the heating is usually not very well, because the heat is conducted only through these spacers, which are quite thin. I mean, there are some problems.
Okay, but we can discuss that when we talk about experiment maybe in the future. Thank you for your explanation.
No, you can just hit us by email, not a problem.
Okay, thank you.
There are contacts on our faculty webpage, so it's fine. This is easy to be reached.
Okay, thank you.
So as we mentioned, you probably got a mail. Sorry, probably for the late call today morning or around lunchtime about our experiment we are going to conduct. But even if you didn't read it or you didn't receive it, it's very simple. We will show you how to deal with the sample put in the chamber and fill it with the gas and do some absorption experiment with carbon monoxide. Because the palladium with orientation 110 is proved to be or is known for the CO absorption. So we have to admit this is the first time we are doing such experiment here, because you would like to prepare for that. However, this machine is so busy that even yesterday and tomorrow there will be experiments, and the next week we start already the CERIC experiment. We still have 2 in June, so it's not easy to find a free spot to try something. So you will be observing kind of like a premiere together with us. So cross fingers.
We switch the camera.
That's okay.
So we switch to second computer, to this measurement one. So maybe I can show you, for example, one example. Well, that already showed you. But for example, this is.
This camera is on.
So you see, here is the sample holder on which we mounted. Maybe better to take it like this.
Okay.
Yeah. So this is.
Wait.
I think.
Why is that?
Yeah, because again.
We didn't hear what you were saying in the last 3 minutes.
But why nobody?
Yes, we did. We wrote in the chat box.
We actually.
But we don't see chat, just nobody is just in front of it. Well, better just to switch on microphone. Try to interact. I mean, speaking is also good.
Okay.
Okay.
It's,
Okay,
it gives us better feeling. But now it's okay.
Now it's fine. Yeah.
So,
Yes, we
so
can hear you now.
You take this sample, you load it to fast entrance chamber. I mean, I did it before the start. I mean, before this session. So I just want to explain you how it starts usually. You mount the sample, you load it to the fast entrance chamber, which should be first vented. Then you evacuate it, wait 10 minutes until the vacuum is relatively good. Then you can open some valves, and using all these several transfers like this one, and there is another one. Here, I mean, it's maybe not seen so well, but anyway. So then you transfer the sample to first to analysis chamber. In that analysis, first to preparation chamber. Yeah, first to preparation chamber. In that preparation chamber, you can somehow, I mean, change your sample. Yeah, it means you can sputter it, you can clean it. So this single crystal of palladium was sputtered and annealed before. Yeah, so now it is in analysis chamber, and we would like to move it to the NAP cell now. Yeah, okay, so it is clear, I guess. Maybe we can switch to second computer, yeah, Brett, and maybe
Okay,
we can show you how these all manipulations, I mean, are done. So for this, I will stop. And start the microphone.
This one. So it's more complicated to have two. Okay, now we are sharing, but now we cannot see. Wait.
Okay, you switch off the microphone there. Okay. Right.
Okay, wait.
Okay, guys, can you see the share screen from the second computer?
Yes.
Yes,
Okay.
yes.
And sound is good because we tried to start another microphone and it started to, I mean, to overlap with this microphone, so the sound was.
So you can still hear us?
Yeah. They hear us
Okay.
with this camera.
I noticed right now there was so I want to show you something, and because it takes about 3-4 minutes, I can answer the questions I noticed in the chat. So now we have the sample in the preparation chamber. So we have several vacuum chambers connected together. There is load locking situ, and see that.
Yeah, I guess this microphone is.
But
that
this
one
camera
is
is on.
Camera is.
Check. I think it's.
I think it doesn't matter. I mean, camera is off because you see here. I think camera might be off, or I don't know.
Okay, probably off. I don't know why.
I don't know. Try to switch it on. Let's see here. And now on. Doesn't matter. I guess.
Okay, we tested a week ago. It was fine. Okay, now, but it's there, right?
Yeah. So you
Okay.
can.
I think the best is just to switch on this, but share the screen from here. That's possible, right?
Yeah, I think you share the screen there, and you can speak to this.
Okay, let's do it that way. If you see us talking, then you cannot see us, or you cannot hear us. Please let us know. Okay, yeah. So now the sample is in preparation chamber. You can see a little diagram here.
In order to switch, I guess you should bring it to this in order to show you. I don't know. And try to switch.
Wait. You know what? We need to switch the screen. It's a very interesting system. Okay, new share is this one.
Okay, so because we have 3 monitors on this measurement computer,
Two
and
cameras, 2 people,
3 monitors,
and a big machine behind us. Okay, so it's a challenging task for us. So enjoy. Must be entertaining, I guess.
Okay, one question. So is this LabVIEW, or it's within the program, that the software that you sent us to
it was
download?
provided by a company, by Specs.
That's the Specs actually.
Specs. Oh, so it's Specs LabVIEW, I think, because it reminds me.
Maybe it looks like LabVIEW, but I don't think that we have.
I think
It's a pen. It's like the analog. I mean, like a similar program.
Yeah, but you cannot program here. It is look like, or I don't know. I mean, we never tried, and it is. I mean, I have some experience with LabVIEW, but here.
Well, when we need something, we usually ask Specs. If we need to do something with the software, so we don't do this. This is the thing actually we don't do by ourselves. The software related things. But however, with the machine, like servicing the pumps and even Michel's experience fixing the X-ray source, fixing. So those we are able to mainly do by ourselves because it's faster and cheaper as well. And it's, we are more efficient if we can do by.
Yes, but one question: when somebody dies, like a gauge, pressure gauge, or well, it's not a good news, but I'm just asking. So if somebody something is replaced, is it this software can automatically recognize the new element, the new?
You mean this one?
No, I mean. If you connect a new pump or something, you need to change. For example, we connected here. You can see that we connected the transfer chamber pump is now inactive because it was broken. So we connected their new pump, but it was not easy to connect it to this software. So it doesn't work so straightforward. So if you want, you need again to contact Specs. Usually they connect it through the remote control and do it. They do this quite fast. But I mean, by ourselves, it's usually difficult because you need to change there some number and everything.
Yes. Okay.
I mean, this software, it's called SpexLab Prodigy. It has also, for example, another. It has several like sub softwares, and one is called SpexLab Devices. And exactly in that devices, you can change different properties of device. So in order to, to change it, you should be sure what you are doing. As soon as you change something and you forget it somehow, and then it might stop completely working. For example, I tried to connect the pump by myself recently. It was not easy, and I did not succeed with this. So I think we should contact soon the Specs, but we try usually not to contact them very frequently because
it's expensive.
To bother them so much. So if we have some problems, then we write just big email. Okay, guys, we need your help. Can you help us? And they usually do this.
Okay. So you are now waiting for the pressure to reach the right level?
And actually, pressure is already good. I mean, everything is pumped, so we can start to move the sample down.
That's what I wanted to show you.
What you wanted to show?
Here, yeah, exactly. To send the sample down, you can see here is kind of the diagram. Okay, you see here the load lot. We put the sample and transfer. This buffer is electrochemical cell, preparation chamber, and now the sample is on the preparation chamber, and we are going to move it from here to here.
For this, you have to open this valve, of course, between two chambers.
And that actually has to be done manually by ourselves because there is no software for that. However, now we need to share this screen. And here you have a cell manipulator, prep manipulator, not manipulator. So prep manipulator is the big one behind us. It moves it from the preparation to analysis chamber. There are, you see already like the pre-installed positions. We can change those numbers. So we go from transfer prep to transfer analysis. You always have to double check the gate between those two chambers is opened.
And this temperature, sample temperature, this is in the analysis chamber or in the preparation chamber?
Now it's in the preparation chamber because I just did a annealing of the sample to 900 K and it is cooling down now. So it is why and you see that as soon as the
Temperature drops, the pressure improves. Okay.
the pressure increase because of movement. As soon as the manipulator is moving, it creates some background. Something dissolves.
Yes.
Then you see some increase of pressure, but still it is in -9, so it's not so big. So you might see that it's quite slow process. Now the manipulator is slowly moving. It is operated by step motor, and it takes like 1 minute to move down. Then when it's down, there is a so-called wobble stick. So this is a small manipulator with which you can take sample in vacuum, remove it from manipulator, and it has quite many like free. You can easily manipulate with the sample inside the chamber using this wobble stick. So we will take the sample.
It will be difficult to show now because the camera is connected. But I would like to use this time and answer Andre's question of how do you prepare the powder samples. So there are several ways, and it also depends if you want to heat up the sample or not. If you want to do just pure analysis, either in ultra high vacuum or in water pressures, whatever pressures, other liquid pressures at room temperature, you can simply press the sample in indium foil. That works quite well for most of the powder samples we deal with. However, for example, if the powder is very fine, for example, graphene, so that it's almost impossible to press it on anything because it's so fine. You press it, and the moment you take it out, whatever the indium foil or any other mesh, it just fell down. But most samples used for catalysis are actually very well okay. But very probably you would like to heat up the sample as well, the powder sample. In this case, we use different meshes. We have a stainless steel mesh, and we also have, and this is probably the most one used one is a tungsten mesh. You just cut with scissors, vacuum scissors, little square, like let's say 7 × 7 millimeters, or even smaller. Put a little heap of your powder on it. It's usually, I would say, even like 0.5 milligram would be enough. It depends also on the density of your material. And then you put it in between two waiting papers, and we have a presser that we press the sample inside this mesh, and then we spot weld the mesh in the sample holder we showed you before. We put it inside, and we spot weld the thermocouple on the sample holder as well. So you have good connection, good contact, and it works perfectly. We have good experience with measuring for the sample, and it just doesn't even fall down from it.
So now maybe we can try to take this camera, if it's okay. I don't know, it's too short maybe. Can you move a bit with computer, maybe several? So maybe you can see something there. Yeah, there is a window. Yeah, and in that window there is a manipulator. So Brett now is going to use this wobble stick, which is, as I said, used for taking sample. I don't know if it's seen, maybe not much, but you take the sample and you see the sample here. Yeah. So it's not seen very well, but for example, I already took the sample from UHV manipulator and put it to
on the wobble stick.
On the wobble stick, yeah. So now the second thing is to remove manipulator from analysis chamber up back to prep chamber.
So now we change the screen, right?
Yeah, I think the screen is correct.
So this one.
Yeah, that one.
Okay, so now again, I go to prep manipulator and move it. I just move it 10 centimeters above. So that's definitely enough for the cell to be brought in. So we have a sample wobble stick. It's waiting for the cell to be brought to the analyzer. And since it is there, we dock the cell to the analyzer and put a sample inside the high pressure cell. And since then, you can actually observe everything from the measurement computer. There is a camera. You can see the sample. You can see even the nozzle, so you know how far away are you from the nozzle to avoid the touch. And we can set up the sample to the measurement position and start measurement. So, if there are any questions, please go ahead. So now, manipulator, there's a cell manipulator. You can bring the cell to the manipulator. You can see there are only two main positions, docking, and it's the load lock, which we track it completely for service, or when you want to have a dual vacuum in the analysis chamber, so we just move it out. So now I'm going to use the docking and bring the cell close.
Again, should be sure that the gate valve between chambers, which is called in situ load lock, where the cell is normally stored, and the analysis chamber is open. Because if you forget to open the gate valve, of course, there can be some.
Okay. So I think, Michel, it's very difficult to see with the camera. Bring the sample in. I will answer just a question about the powder sample.
Maybe I can
bring it in, and we just.
You can also maybe open those photos in the presentation, which shows the cell from close distance, and then people will understand what we are actually doing.
Okay. So go ahead. You can prepare it, and there was also the other part of the question. Yes, of course, you can use a tape as well for the powder samples. However, again, it's the same as with indium foil. You cannot use it for high temperature experiments. It can be done when you want to do some measurements in different environment, but only room temperature. The indium melting point is about 154 degrees C. So theoretically, you can still heat up to 100, let's say. But for the heating, whatever, we always press it in the mesh, and we have very good experience based on that. You can also use pellet. If you have a pellet that is actually quite strong, it's very well pressed, and your material is conductive, then we can just put the pellet on the sample holder and use those stripes to cover it. Of course, you cannot screw it too much because you would break it. So mostly people are bringing the powder is in a powder form, and we are pressing it here. The other way is we have a one sample holder, which is exactly this kind of shape, and there is a small hole drilled in the middle, and it's about, I don't know, 3 millimeters in diameter, and you can also put the powder in, and again put it in between two waiting papers and press it at, like, we usually use 80 kilonewton with our presser, and put the sample inside, and then it doesn't actually get out. You can heat up the sample, you spot weld it, the thermocouple close to the hole, so everything is in a good condition, good contact, and that we also did some work with that, so that's also possible.
Okay, yes. So sample is the cell is in the analysis chamber. So
you have to share the screen, Michel.
I think it's shared.
No, I can still see this one.
I can share just to explain what I wanted to explain. It's this. Okay, so you see this is the photo of this analysis chamber. So normally the cell was in this chamber. Yeah, it is. There is a manipulator, so it was retracted, so you could see this the cell through this window here. Now, after we started to move the cell, it is now moved through this gate valve, and now it is in the analysis chamber. So when you look in the window, I mean, you see the cell is like here. It is still not connected to analyzer here. It is like a bit retracted now. However, I mean, in order to dock to analyzer, we should do it already with a joystick manually. It is not done automatically. you should press it somehow with filling, and then there is a special locker here which you should pull, and then it locks cell to analyzer. So it locks it in a way that it seals very well. So when you will fill the cell with the gas, it would not leak out from the. So I mean, this connection between analyzer and the cell is rubber sealed. So when you press it, this rubber ring is it seals. I mean, quite well the pressure. So it is this wobble stick which you use for opening the door. I mean, this is the connection, and for taking sample. This is a bit of UHV manipulator scene, which was, I mean, moved up by 10 centimeters, as the same as Brett did just seconds before. So now, I mean, when the cell is close to analyzer, we can go back to this screen and I mean, try to do this docking. I mean, to connect the cell completely to analyzer and to lock it. For this, you should first send it into position, use the NAP manipulator, already another manipulator, which is already used for operating the cell inside. And there is a position called docking. So we move to docking position. And then by using such a joystick, which is here, you operate all this manipulator manually. You look on the in this window, which I showed you just before, and you try to press the cell to analyzer. So this is some mechanical things. Usually when we do experiments with somebody, I mean, all these operations are done by us. I mean, users, they don't do this. Also, other colleagues which work with us here, they usually don't do all this manipulation with sample and cell because it's quite dangerous, quite easy to break something. However, I mean, just to understand how it does, it is done, it's I think good. Okay, so we lock. So, I guess now I can show you another screen where you see the camera which now looks inside the cell. There is a camera, there is a one window from side, and through this window you can look inside the cell. So this is the enlarged picture of the nozzle, which is connected to the front part of the cell. You
There is the engine, there is motor, turbo start.
Stop motor, okay. Okay. So Brett is now manipulating with the cell. You see that the nozzle, which is actually part of the cell, however, I mean, it is moving a bit when you press the cell, when you a bit release the pressure and so on. And now, after we have connected the cell, we can insert the sample to the cell, lock the door, I mean, close the door, and then approach with sample to the nozzle. So this nozzle is actually the aperture which collects electrons. So here we make some marks usually, and then because sometimes there is not enough light inside when you approach with the sample. So, okay. Okay, so you see now it's in proper position, so quite copies the marks which we did before when we did some measurement. So we should, when we will approach the sample, at some point we will start see sample here, how it's approaching. And at some point we start to see the shadow of this nozzle on the sample. And I mean, as I told you yesterday, this shadow and the sample and the nozzle, they should never meet. Because if they met, it means the nozzle is touching surface. So it's quite dangerous.
Just one more question. So you always approach with the nozzle to the same distance compared to the sample?
It is, I mean, because you should understand, for having a good signal, you should fulfill some condition. And the condition is that you should, I mean, send the beam just in the one point which is in front of this small aperture, which has size, as I told you, 300 microns. And as soon as your sample is a bit farther or a bit closer, the beam comes with some angle. So it tells that it will irradiate a bit, not exactly the position in front of the hole, you know, and then you have a very low signal. I mean, we do this alignment, fine alignment, after we insert the sample.
Yeah. So because this is so complicated, you don't have the option for changing the angle of the sample compared to the nozzle.
There are only movement close to aperture and back. There is no way.
Just not the angle. So there is no angle resolved XPS possible.
No.
Okay.
You know, we have here only the, if you want to change the probing depth, so we use X-ray source, which is aluminum alpha with energy 1.40.
1486.
Yeah, and then we have also UV source, ultraviolet source. So
yes.
You can also see some molecules, but of course, I mean, valence bands are not so easy to analyze.
Yes.
It's not used so often. Okay, it's okay, Brett. So I can send now.
So we can bring the sample in. So it should be
Brett put it in the sample in. So now, I mean, as when you introduce the sample to the cell, the sample is usually quite far from the nozzle. And now by using the movement inside the cell, I'm starting to approach the sample. For this, I can do first like quick approach using like a software. So I go to position which is called manual approach. So it should stop there are some units like 24 millimeters to 2 centimeters far from the nozzle. And then the last 2 centimeters usually again should be approached manually. So software has some protection, so it would not let you to approach closer using software. Just in order to be safe, you know, this is for safety reason. If you have very thick sample, somebody can want to measure like a sample which has like 1 centimeter thickness or so. So, I mean, the sample then can again break the nozzle, and the nozzle is quite difficult to replace. It is expensive, so it is quite a headache if you damage the nozzle. And it is very sensitive. It makes from copper and very thin copper, because they wanted to make this small hole. So as soon as you just touch it, don't need even press, it is already blocked. And it's all. I mean, you need to take it out somehow, maybe deblock, or maybe to use some drill to fix it. I mean, we did it twice, and I mean, it was not very pleasure. Okay, so it is approached. I guess now I can again switch to camera. So you see now there is not much light inside, because it is in a position when some shadow comes. And I'm approaching now manually. So you see now sample is approaching to the nozzle. There is also problems with light.
It's just
I mean, at some point there is a big reflection from sample, so we can do auto contrast. So I guess now you see the single crystal. There's some screws which are used to fix this crystal. So we approach. Okay, there is still no shadow. Okay, here I start to see some shadow. However, there is another screw which a bit complicates the situation. But I guess we can move it a bit up, like this, and it's like this. Yeah. So as I said, we have some marks which tell us the distance should be the same as the size of the aperture. So size is 300 microns, and the distance is some 300 microns, more or less. So you can see that it somehow corresponds to this distance. I mean, this distance to the shadow should be actually double than this size, but the hole is a bit smaller. It's like this. So here you have like a more or less double distance, because there is a mirror. So the actual distance surface is somewhere here. So also the beam is irradiating this point on the surface. Okay.
Well, you can start the X-ray source.
You can maybe start the X-ray source.
Is it it's on? Oh no.
It's completely off, but we need to wait a bit, I guess.
It's okay, I can start.
I can share again the say. So now we would like to first measure maybe clean sample. It means to do alignment to find a good signal
In vacuum.
in vacuum, yeah. And then we will dose some gas and do again the measurement in presence of gas. So for this, you again choose the SC'21. This is the name of our X-ray source. And first you need to do warming. It will take some time. Also the chiller starts, maybe noise will be a bit higher.
But if you have any questions, now is a good time. Either it can be technical or anything.
Because it takes like 10 minutes to warm everything. So I mean,
you're too busy by explaining that we forgot to start it on, but this is the process that it's normally, we done this in the morning, and then we usually put the X-ray source to standby mode during the measurements, or when there is some kind of like a heating, when we don't measure. So that's what it is done usually, that you start the X-ray source in the morning and keep it on the whole time. Unless you put standby mode.
Maybe we can look at this software. I don't know if somebody of you installed this HERCULES fitting software, which Brett sent.
Yes, I did.
You did already.
So we can maybe share this second screen, which we use for spectral processing, because we will measure some spectra of palladia, which we already have here. So I mean, so maybe you can.
Oh, you mean did I open it?
We can open it. Can you share the screen here?
The thing is that if you don't have installed the software, how can I do?
I don't know if we can both share the screen. I think only one person can share the screen.
Let me try. What about this one? It is open a new window.
So we'll share always.
It can be seen. Can you see the?
Yes,
the
we
curve?
can.
Yes.
Okay, so after we finish measurement on that specs, we export the data, and you can actually there's several options where to export it to either XML or RAMAS, XY, ASCII. There is depends on what software are you used to. We for a couple of years are using a software which was developed by our colleague, the former student of our faculty, our department, and our group. So it's quite convenient, and but the basic principle is the same for any other software you are using. So there's always a couple of functions that can be used for fitting. Here you can even choose from purely Gaussian or Lorentzian. For the XPS profiles, it's usually a combination of Lorentzian and Gaussian profile function. And you can use the void, which is another kind of like a combination, or there is even Dunia Shunjic, which is function used for asymmetrical profile shapes.
I think palladium, because here you see that we opened some file where we measured already palladium some time ago, and actually now after measurement we should actually receive some spectra which are kind of similar to what you see here. So first we will measure survey scan. You see here like palladium peaks. It is palladium 3D. I think this is 3P, and there are some I think 3S and so on. For us, it's interesting is palladium 3D. This is the characteristic peak for palladia. Yeah, I mean, I can maybe delete all these fittings which we tried. So we can measure it as a doublet, but usually it is quite difficult to fit doublet, especially if it's asymmetric. And in case of palladium, it is kind of asymmetric. I think this comes from its nature. So in this software, actually this software was developed not only for fitting XPS spectra, I mean for finding the states, I mean which actually contribute to the spectrum. Yeah, it was also developed for operating some analyzers and some manipulators. I mean this guy was quite good in programming, so he tried to build something that we can, for example, use this software in the same way as a Prodigy. Usually we don't do this because this is, I mean, you need to work a bit to connect special analyzer. However, it is possible because it has here different functions for different motors. I mean, as soon as you can, I mean, you know, some like how to, I mean, how to connect this, then it's not a problem. For example, in Trieste at MSB Beamline, it is quite frequently used when you do RPS or when you do some exafs measurements, so they use it. For us, it's more interesting this function, which is called here fitting. So in this case, you choose whatever spectrum you want. First, you need to open it. I'm sorry. You need first to open the file which you measured, and then you have the number of spectra which you measured, the detailed spectra. For example, for us, as I said, interesting 3D, yeah, palladium. It looks like it's shown here, and you can fit it. It means you can try to find profiles which would actually, I mean, show you which oxidation states, because in this case it is pure metallic palladium. However, it contains small signal from some surface atom of palladia which have a bit different shifted peak doublet. Also bulk palladium. Also then can be some chemicals on surface, like some gas, or not gas, some carbon, and then all this would result in different doublets which actually overlap, and then they create this profile which you measure. And for XPS, usually you try to, I mean, like detect each individual state which you have. So for this, first you need, as Brett said, to cut background. I guess maybe some of you are familiar with fitting of XPS spectra.
You can ask if it actually makes sense to go through those.
If everyone is familiar, then of course, I mean, we would not explain this because this is basics, which is like usually, I mean, people know who works with some XPS machine, you know. So you measure spectra, then you need to process them. You need to feed them to find states, I mean, and so on. So do you have
I haven't done the full overview of the software. Is the library of elements also included, or it's separate from the software?
Yes, they wanted to include it somehow, that guy, because he actually, he moved from our group. I think he included sensitivity factors. So when you do some quantitative analysis, you can normalize spectra directly on sensitivity factors, or maybe on cross sections. And I think there was idea that he wanted to include the library for example, Specs Prodigy, it has its own library. So after we measured the spectra, you can choose elements which you have, I mean, which you expected to see on the spectra, and you will automatically see all peaks from those elements. As soon as you see some additional peaks, you can start to think, what is this? It might be something. But here, I guess.
However, the good thing is that if you write him and you have this kind of good suggestion, he's able to incorporate it in the software. You can also write that you were listening to this HERCULES school, and those two guys from Czech University were talking about this, and you like, it might actually help to make it faster. And he can incorporate in that whatever we have suggestions. I've experienced that we wanted to do something and it was not part of the software, so he was working on it and put it in, because this software is used in Electron as well, in synchrotron, and as well as Spring 8 in Japan. So
they abandoned CASA completely for XPS. CASA is not used anymore.
CASA is used by many people. I think CASA may be more popular than this COLIX
for
PD.
Sure.
For sure. I mean, almost everyone who works with XPS, he knows CASA. But somehow in our group, we started with COLIX PD. We found it even more convenient. And very often when we show users here that you can use this COLIX PD instead of CASA, they find it quite convenient and even more easier than CASA. But of course, yeah, CASA is another way. CASA is free. This software costs, I think, some 200 euros. It's licensed for whole life, I guess, for one computer.
400, about 400 something. It's not too expensive.
Depends. I think
Depends. Maybe for students, 200 for
even less. Maybe it's very academic. I think it's less. It used to be like.
I think he has there some prices. I have to go.
Sure. So, as Misha said, this profile is not actually easy. And as I showed you today in the presentation, we deal with platinum mainly, which is similar. There is also 4F doublet. It's also asymmetrical. And even if you have a small nanoparticles of platinum, there's additional doublet added in the spectrum. And the background, because if you have a look on the survey spectra, so the background is a typical background for photoelectrons, is actually lifted by many inelastic collisions, and also by the photoelectrons for the elements. So you have to kind of subtract all this if you want to actually start fitting. And for this purpose, there are three elemental backgrounds in HPS. One is a linear background, where you just to put the starting and ending point, and you put a straight line. The most that is sometimes when it's when you have like quite difficult spectrum or very long one, for example, for cerium, that or cerium oxide, the spectrum contains 5 doublets, 3 arising from 4+ and 2 from 3+, and the window is quite broad. It's like from 920 to 880, so it's like 40 electron volts. In this case, it's quite difficult to use Shelley background, which is probably the most common background in HPS. And the third one is a Tugart. For
Yes.
Tugart background, you probably know. You preferably have to incorporate kind of like more space in between the spectrum itself, and it's based on that you can also calculate the shape of different heterostructures on your surface, and it's quite useful. But honestly, we are mainly dealing with Shelley background. Once in a while, we have to use the linear, and it's enough. So if you
So sorry to interrupt you. So you never use Tugart?
sorry.
You never use Tugart background fitting, or you sometimes you do?
No, you always have to you have to subscribe the background. That is for sure.
No, Tugart. I mean the fitting
Tugart.
of the background.
Oh, yeah, you need to have a special software, or at least you used to have. I remember as a student, Tugart actually came to a department, but here is not.
Once we discussed this, I guess I don't know how somehow it.
No, because we have a special software just from Tugart, who was here a couple of years ago to give us a talk. However, I have never, personally, I'm sure I've never used it. So we always use
I have it somewhere on my computer. He was following us that using this background, it was possible to find thickness and some structure of the layer and so on.
That's right. So you just click if you want to do some analysis. So you pick up whatever you are going to use. So it's a linear background. You see it's a line, and it goes from one point to another point. So this is not very well done, as you can see. There's an error, huge error here. You need to choose a point somewhere here, or you just simply choose the background, which is more precise from the physical viewpoint and from the nature of the spectrum.
The background is not always correct sometimes.
That's right. And then you have plenty of functions you can use if you have a single peak, like for example for the SCO level spectra, you are using kind of the combination of Gaussian Lorentzian. You can somehow find the function that I actually use for those names here. The Benjamin that you mentioned is asymmetrical peak. The Benjamin is convoluted with Gaussian, and then different like a combination. And then there are doublets. When you have a doublet, like for DEF spectra.
You can fit it as doublet, or sometimes we prefer to fit only one part of doublet because then you're more precise with background, and then but you answer the same question. I think you can use here, try to use some of this asymmetric peak. Maybe maybe this. you see that you can create quite good heat. However, the background is almost zero, and it is not, of course, correct. You should have some
Okay.
like this. Yeah, and let's try another profile. Let's just, it's even worse. It means you cannot fit it with one profile. In that case, you need to add more.
Another peak.
Because the principle is, I mean, if you don't know anything what to expect with your sample, so you try to use the less number of peaks as possible. So this is the way how, because as you use more and more peaks, of course, you would get a nice fit. I mean, that the productive line which is created by those peaks will be very well, I mean, overlap with the measurement data. But of course, to explain all those peaks, it then becomes quite difficult.
Yes.
It means if you expect to see there like 3, 4, 5 peaks, you can put them. However, if you don't know what to expect, and in case of pure palladium, I would expect just to have maybe one bulk, one surface peak, and maybe some small peak from adsorbate, yeah, because it's I mean, always that you would have some adsorbate on the surface, usually even I mean, especially in case of NAP cell, because NAP cell it is a cell, it is chamber which is not baked usually, yeah. So
Okay.
you cannot clean it as UHV chamber.
Perfectly, like other, yeah, okay.
Pressure inside the NAP cell would go maybe maximum to 10 in -7 millibar. And this is already quite poor vacuum for such sensitive samples as palladium. So in several minutes, you would have at least 1-2 monolayers of something on the surface.
So how do you clean the analysis chamber? Do you maybe purge with argon or with some gas?
Yeah, we clean the NAP cell by purging firstly by oxygen. I mean, between two experiments. If you have one experiment, and for example, at each step you use the same gas, I mean, you don't have much time to clean every time the cell. So it means you put the sample, you evacuate it, then you add another gas, and it's like this. However, between two different experiments, we always connect the cell. We fill it with a relatively high flow of oxygen, and then anneal the cell. I mean, they heat the stage, you know. So we can heat this stage where sample is to like high temperature to 500 degrees C. So we can keep it overnight sometimes or several hours. So this helps to more or less remove all carbon contaminations. And then it can be also purged by argon for a short time to remove oxygen. And this is the way how we try to get the clean cell. But of course, as I said, it's not like UHV. But as I said, I mean, as soon as you start to dose there some gas of high pressure, usually you would always get there a bit of carbon contaminations, and this is always happens also in real life. You also have catalysts which works in ambient pressure, yeah. So I mean, as soon as you increase pressure to 300 degrees C on your catalyst surface, usually all these carbons are somehow burned by oxygen, and then you add another gas.
And they evaporate, they are volatile, okay.
But of course, at the beginning, when you just try to measure first step, the clean sample without gas, you always have this contamination because it's unavoidable.
Okay. So just another question. So how do you do calibration of your work function? Do you measure the work function of gold, for example, to calibrate the energy?
Here, gold and argentum, silver samples. We have two reference samples, and from time to time we measure silver 3D spectrum. For this, we use it for because it should be symmetric. So this is, I mean, we measure the profile and try to see if our peaks are symmetric, if there are no because when you move with monochromator and you do some calibrations with the detector, usually you can have the situation that somehow the channels are overlapping, not in a good way. So you would have a bit asymmetric peak. So I mean, silver is used for change of symmetry and also intensity. We know what should be the signal from a silver surface, clean silver surface, when we have some photon flux. I mean, like 40 watts or something. So we check if the intensity is reasonable. If intensity is very low, it means that from time to time we need to change the anode in the X-ray source. We already did it once. So because as we need to have very focused beam, to get the beam with a size several hundred microns, it means you should, have the source of this X-ray also very small. So it means that the anode is bombarded by very focused electron beam. So usually you just make a hole in the anode, and then it's, you just evaporate all aluminum, make a hole there, and then the signal is quite low. So we test it from time to time, and another sample is gold, as you said. So we measure Fermi edge and check if it's in zero. Sometimes we have a bit shift, like 0.2, 0.3 eV, then we, change in the software.
Correction, you include correction. No, okay, that's fine.
Okay, I guess it is prepared now. Maybe we can start the alignment. Maybe you can do this slide, as I speak too much. Okay, so first of all, after the sample is in, we have to you can start sharing the screen again. Yeah. So you see the X-ray source now is on, it is green. You see here the parameters which we use. This is quite nice. If there is any problem either with pressure or something, so those items I still use became the red. So if you know, okay, there is something, some issue we need to deal with. When it's in the operating condition, it's yellow. So if it's a standby mode, it's gray. And so direction someplace. Yeah, okay. There's cannot be here. Let me know. So we do the. I didn't open the file yet, right? Okay. So you can say new file, or maybe open Palladium. You can open the previous one and it's Palladium. We're done with go to Rockstar. My folder. There is Palladium. You can open one of that. So usually we open one old file with similar spectrum regions. So then we can just copy the groups and not to create them. Not to because you see there are many parameters like the region in which you want to measure each peak and so on. So there is to create it from the beginning, it takes quite a lot of time. Much better just to okay. So save it under different name. Now you can figure out the data and use it here. So the alignment is usually down on the peak that is okay, this is not the case. The alignment is 335. Alignment energy. This is where the radium is the maximum. So it means that analyzer now is set in the position when it detects only electrons with binding. You can switch it also to kinetic energy, but the binding energy of these electrons is the same as the peak of palladium. So the intensity should be the highest on the spectrum. And you see some signal. Maybe for this you need to switch to another window. So, all right. Here. So it's already set up the analyzer on this kind of constant energy. And there's one more thing. Maybe I first
Okay, no good. It's the same value. All right. Now there are two kind of like a screws for changing the position. It's those two are in the on the monochromator, and I will check if you can
Try to switch to counts per seconds.
do it.
So I was moving a bit with the beam. So we have a monochromator, there are mirrors, and there are some regulators. So you can rotate them a bit, and you can move a bit with the spot on the sample. And I was trying to put the spot exactly in the position when the signal is the maximum. So this position is actually when the spot is in front of the aperture. Yeah.
So you are looking for the maximum intensity?
Yeah, just maximum intensity. You try to find the maximum intensity because maximum intensity means less time for measurement.
Yes.
Also, I mean, yeah, this is just yeah.
Sorry, just a question. What is the power of the
40 watts now.
40 watts.
We used 150, but then after less, maybe then 1 hour, 1 year, we just damaged the anode. And then Specs told us, oh, you used 150. It's like, you know, it is there, so you can use it, but we do not recommend it because you just evaporate all aluminum because the anode is actually made of argentum, of silver, and there is some 100 micrometer thick aluminum layer. So you irradiate this aluminum layer by electrons of high energy, and you have this characteristic X-rays, yeah? And then they said, okay, you just simply evaporate maybe this layer. And we replaced the anode, and we took that one, look on the CM, on the microscope, and we saw there a big hole, like 1 millimeter crater, deep, like completely, I think, up to
ablated, actually. Yes.
Yeah.
Okay.
You don't have any more aluminum, so no aluminum light. So now we work or 25 watts or 40 watts. This is we still have quite good signal, but of course. So okay, so Brett finished this alignment. So first we move a bit with the beam. Then we also check the potentials on this electrostatic lens, which actually keeps the electrons in the analyzer.
Yeah.
I mean, in this differential pumping part. So
so this the maximum current from the analyzer is actually regulated by the software, or you can adjust the lenses.
It was not seen. It was done again on this. You can switch back to this screen. So here you again have Phoibos analyzer, and here you have this pre-deflective Y and X, so you can deflect the beam inside the beam.
So you can do it. Okay.
The
voltage is on this deflection
lenses. So you can
to direct the beam a little. Yeah. Okay.
And then you again watch the signal and try to have them. So it's like you increase the transmission function.
Yes. Yes.
Okay, so you can switch back. So now is the survey is being measured. Yeah. So usually we should have. Yes, we can delete all this UPS.
What is this for? I know, but there is kind of like,
kinetic energies. I added because oxygen peak and palladium 3P are overlapping. So it was not possible to follow oxygen normally. So for this, I set for the OSHA peak of oxygen. So here we measure also not only oxygen 1s peak, but also oxygen OGE.
So let's see how the sample is clean now, because based on experience, even if you put a sample in the chamber from the previous experiments, the inner walls of the high pressure cell might be contaminated, or can be sick something. But at room temperature, there should not be too much. But the longer the sample is in this kind of like a not very clean cell, the higher chance there is something sick on it, so absorbs the surface.
So you might see here is this library which you asked for. So here you can choose by pressing on this pictogram here, you can choose what elements you want, and then automatically you have all peaks from those elements. They are assigned here. So you can see. So you see here is palladium 3D. No, it's palladium CS. That, and then you see that there might be a bit of oxygen, some small wave here, but mainly signal will be from palladium.
Looks like it's yes, soon, because the oxygen peak 1s level spectra is around 530.
But it's overlapping.
At the same time, there's a +5.
You see here, so they are completely overlapped. This oxygen 1s and palladium 3P.
So it's good we have the palladium. It's a good sign. We are on the sample. Yeah, it's a nice peak. To compare with the spectra from the lab books, from the handbook, it looks like this.
Normally, this is not the characteristic peak for palladium. I think the characteristic one is this 3D, which one is usually measured and used for analysis.
It's mostly the one with the highest intensity. It's only influenced by the oxygen.
So actually, you can in this software, when you do measurement, you can change many parameters. So here in this experimental editor, you see you create the group with survey. Then we are going to measure palladium 3D, oxygen 1s. However, it's not oxygen 1s. I think it should be called oxygen 1s plus PD 3P, something like this. And then you can change parameters such as step. This is how many points. I mean, you understand what is the step on the spectrum. So yeah, when the measurement happens, you know, so with which step the software is changing the energy and measures intensity. Yeah? Also, you can change the dwell time. Dwell time, it is as soon as analyzer is changing the measuring energy, then it should wait there some time. Yeah, so this is dwell time. I mean, the time which the analyzer waits at the measurement point. So longer time he waits, more electrons he catch. Yeah, so then the signal becomes higher. But of course, then the spectrum is measured much more slowly. So for example, we prefer to use a lower dwell time. It means like 0.1 second or whatever. However, more scans.
More scans.
Yeah, some people they use higher time.
Longer dwell, but one scan. Okay.
Yeah. I guess this is the same. More scans, smaller dwell time, you get the same quality of the data. Because important is only the time of measurement.
But just one question. So when you have the final spectrum, when you set the low dwell time, but you have many scans, can you actually save individual scans, or they are all added automatically?
Possible to extract each individual scans. You can, extract all of them, try it somehow in a software, because usually one scan is quite noisy, so it's quite difficult to save one scan, but you can, make a sum averaging of every 1, 2, 3 scans or something, and compare this. You want to see some dynamics.
This is actually also very useful. Oh, there is one more point for the group measurement, which
already switched it there. It's here.
Okay.
Always
so even somewhere else. One thing, if you open this here, there is like a processing order. Now this is in consecutive, which means he takes the first line and he completely measures. Then he goes for palladium, you measure 3 scans, then go to oxygen, carbon, like that. If you change it to cyclic, in cyclic mode, you measure, you measure one sweep, one scan from each element, and then it goes back. And then you measure second one. Then you go here and you measure third one, as the final one. So in the second round, it goes to here and just, measure those. So it's kind of cyclic mode. It's useful for if you have a catalyst that is actually changing, and you want to see the changes within the time, because it might be, the changes might be like within 10 minutes. You don't want to spend 10 minutes measurement on one element and then you
miss the process, because if it's time dependent, then you don't catch it if you do the first. Okay.
I guess we need maybe only one scan for palladium.
And also those sweeps, if you have a sample that is not conductive, but it's charging, and even charging within time. So it means every sweep would actually be a different position, and then you see the summarized, like averaging the result. And of course, the peak would be broadened because of the double charging or this time dependent charging. So this is perfect to actually see each sweep individually. And for example, each of them move to the right position and then do the averaging. Actually, PD can also allow you to see all those sweeps. It's a little bit hard work to do that, but at least you have just the chance to correct the data if you have such problematic samples. So you always have to check if all the sweeps and the scans are actually at the same position, they have the same width. If you are not sure that this is the case, but in this case of the palladium symmetry stuff, there's no problem at all. Of course, it's symmetry, so it's conductive, it's grounded, so you can actually display even in this software on the share. We can display those two sweeps. Oh, there's only one. No, there are two. Okay, I can measure all of them, and you can see the same. It's just the same. There are 2 lines. Now it's measuring
oxygen 15.
Yeah, so there are only 2. So if we have
you can also show each of them. Just sometimes, if you want to see if you have some changes, you can switch between sweeps. If there are more sweeps, you see here just 1, 2, 3, 4, 5.
Yes.
So usually we use sum, so you see the sum of the averaging, of this. Okay, now it's measuring oxygen plus palladium 3P. So you see here you have this palladium 3P peak, and then somewhere here should be oxygen. But of course, there should be not much oxygen at the moment. It's kind of clean crystal.
Oh, I didn't check. What about the carbon? There's nothing. Oh, little.
Yeah, this is negligible.
As I said, I mean, as soon as you put it into the cell, you always will see a bit of carbon.
And it should be a long window because we want to see the gas phase, which is the higher binding energy, and also the absorbate on the surface.
As soon as we introduce, I guess, some CO, here should be somewhere gas phase a bit higher, 535, I believe, or something like this. It will be seen, I think, the gas phase will be a bit apart from this palladium. But the absorbed species palladium, they should somewhere overlap with this. It will be quite difficult. But we have a carbon 1s spectrum, which will give us the same information.
So you will reduce the number of scans.
Yeah, I reduce it because
So if you, as I mentioned in the first hour of this presentation, you can apply through CERIC webpage. It's a twice, I probably didn't mention that, it's twice a year. This kind of like a call for proposals, and you can apply also for other techniques. There's a wonderful TM in Romania. There's this synchrotron radiation, MSB in Electra, and SACS in Prague University or VLS, Technical University in Vienna, in Graz. So you can apply on those for to do the measurements in those facilities. And if your proposal is approved, so the normal conditions, when there is not such situation like it is now in the world, you are able to travel here, accommodate in the hotel, and within those 5, 7, 8 days, do the experiment, to sit here with us, discuss the science, and do the measurements. So that's how it usually works.
Yeah, usually CERIC covers accommodation and travel for expenses.
For up to 2 people, so you can take your colleague to travel for the experiment, and so after that you bring your samples, we deal with it in the beginning, figure out how to mount it, and we discussed even before what kind of samples do you have, because we saw the proposal. We technically evaluated with Misha to be sure that you are not requested unusual temperatures or some abnormal pressures, that it's actually possible to conduct the experiment with this facility without any trouble.
Mm-hmm.
Yeah. If you have any questions regarding the CERIC proposals, or
I think there is a 2-stage submission system. So some people which try to submit the proposal for the first time, they can go to the first call, and in that case, they submit the proposal. These proposals come usually to the staff at the different facilities, and they give some advices how to improve the proposals. Also, if there are some technical things which are impossible to make, I mean, here, for example, then we recommend that this and this should be changed. This pressure should be somehow increased or decreased, because I mean, so based on our experience. And then in that case, proposal then has a bit higher like chance to pass the second call. Always, I mean, all users which are experienced, they can go directly to the second round. And in the second round, I mean, if there is some problem, technical problem, we find that this, it will get automatically rejected. So you don't have chance anymore to resubmit it. Maybe next time, in the next year or something like this. So. Yeah.
Okay, so Michaela, because I saw that for this first half of the year, your experiment was not included in the call. Is it going to be included in the second half, for the second call in September?
Yeah, next, there is a, as Brett told you, we would like to make some update on our machine this year. So first we want to build this fuel cell cell for studying fuel cell catalyst in operando conditions. And other things, we will be quite busy with this new Enviro ESCA, which is planned to be installed this autumn by Specs company. So for this reason, we asked CERIC to stop the accepting proposals for the next semester. I mean, the second half of this year. Yeah.
Yes.
From July to the end of the year. However, in the autumn, in September, there will be another call for next year, which starts from January, and I think we will be there already.
Okay, good news.
So for the gas inlet, I mentioned in my talk that you have like a mixed gas line. You can connect any kind of gas to here. Those flow controllers are actually like preset up to a certain gas, to hydrogen, oxygen, and argon. So if you want to precisely know if you are using, for example, different gas here, like CO or any other, CO2 or whatever, so you have to kind of recalculate through using some constant if you want to be sure. But mostly we are
mostly we are following just pressure inside the chamber. So we are adjusting the flow in such way that we have the required pressure which we want to have. So pressure is for us is, however, of course, sometimes people would like to keep the ratio. So they want to have two moles of one gas and 1 mole of another gas. So they try to set the flow in such way that they keep this stoichiometry. So in this case, we can do in 2 ways, or we can recalculate it using some tables which we have here. I mean the flow. I mean using the different constant, or we can connect the notebook to our flow controllers, and then we need to set new constants for the gas which we would like to use. Usually it takes a bit of time, so we prefer just to use tables and do it here on the table. You know. And then you know that if you want to have 2:1 ratio between oxygen and the hydrogen, however, you use the flow controller which is for argon, and there is a bit different constants, and maybe we can recalculate it here, and we know that we need to use 2 milliliters per minute for oxygen and 1.3 milliliters for hydrogen in order to have this 2:1 ratio inside the mixture, you know. Because you understand that we depending on the flow, you will create here a mixture, and this mixture will contain the concentration of each gas, which is proportional to flows which are used in the flow control. And then here these gases are mixed, and then using a tube which is introduced to the NAPXPS. Yeah. So here, and the NAPXPS has also its outlet. So there is a pressure controller. So, for example, usually we prefer to keep pressure controller is something like a controllable outlet pumping. So there is a device which actually can change the diagram, the aperture for pumping. So there is a pump connected here, turbo pump. It pumps with some speed. However, of course, this speed depends on the size of the aperture which is used for pumping. So this pressure controller, you can set here some pressure which you want to keep inside the cell, and it will adjust this aperture to the such size that you have, I mean, a dynamic mode in which I mean, you supply some gas and you evacuate this gas with some speed, and there is some, I mean, set pressure inside the cell. However, usually what we prefer to do, we try to keep it completely open, so to keep the maximal pumping speed, and then simply just adjust the flows in such way that we have the pressure which we want to use. I mean, 1 millibar or something like this. So this is the usual way to work. So maybe we can open it now. Brett, can I open the pressure controller? Is the manual valve is open? Because always we have also some manual valves together with this pressure control. Because all these flow controllers and pressure controllers, they usually do not seal so well. So for example, if you have connected several gases to this and these valves are open and you keep it closed, still you can have some leak to the mix line of some gas which you don't want to have. So for this, you keep all these manual valves are closed, and you open it only when you need to use the line.
So one more thing, Mr. Can check if we have the format spectrometer running, so we can check.
Yeah. Okay, I can switch now to mass spectrometer.
So this is already finished, right?
Finish. I can start now. Maybe this long one.
No.
So we have a mass spectrometer connected, as maybe I mentioned yesterday, to the first pumping stage. So we can try to analyze the gas which is actually pumped by the nozzle, which together with electrons. You know, so it collects electrons, but also some amount of gas is introducing to the nozzle, and we can do an analysis of this gas. So such as I mean, the reaction takes place on the sample, and the nozzle collects the gas directly from this surface of the sample. Usually, I mean, the concentration of products, they might be, I mean, high enough to be detected sometimes. But of course, it is quite tricky things, and it works not for all samples.
But just a second. So this is only an additional measurement, but it's not really giving the information of whether something is being desorbed on the sample. It's only a small amount that enters the analyzer.
Yeah, only a small amount, and of course there is a big background from
Yes.
the remaining gas which do not interact. Of course, if your sample is very highly reactive, so it means it converts almost all CO, for example, which comes to the surface.
Mm-hmm.
You have a quite good signal from CO2, everything is fine, so you can do this analysis. If your sample is not so nicely reactive, and then usually background from the gas, from, for example, in our case, CO, which is so high that you almost don't see any CO2, or or another case could be that your stage is also quite hot, because to heat the sample, you first need to heat the stage, and stage is usually heated even to higher temperature than your sample. Mm-hmm. And the gases in the cell, everywhere. So it can also somehow be converted on the stage, or the stage can influence the mixture a bit. So then you can have like products which are coming not directly from your sample, but also from the stage and from other hot parts inside the cell.
Yes, yes.
Usually, in order to be sure that what you see by the mass spectrometer is directly from your sample, you first need to do blank experiment. It means to install there, for example, some silica, which is has the same size, which has no reactivity, yeah, so it is linear. Then you measure this background, and then you compare it with this data measured on the sample, and then you can maybe say that that you detect
there is a desorption or some kind of chemical process for producing the volatile components. Mm-hmm.
There's another thing, I don't know if you mentioned, I'll focus now. We have pressure controller. There is a so-called DC pressure controller we have here that can actually pump the gas out of the high pressure cell. You can either keep it closed like it is now, then all the gases coming inside the chamber are actually escaping only through the nozzle. So you are actually analyzing, as Misha mentioned, everything from the stage, the background, the walls, and it's difficult to say where the product's coming from. If you open the pressure controller, most of the gas you are actually evacuating out, and of course we have to increase the flow rate
in order to keep the pressure inside the cell.
Yes, in order to keep it as the desired pressure you want, like for example 1 millibar. So if I put here 0.3 milliliters per minute, the minimum value that those phone controllers allow us to set, doesn't allow us 0.2. So we have like a bypass if we want lower pressure. That was one of the idea of Professor Ernst Bauer I mentioned during my talk. And if you want, if you open this pressure controller, you have to kind of like put higher flow on the flow controller to get the feed the cell. But in this case, most of the products or gases coming in the nozzle and analyzing by the QMS are actually coming from the vicinity of your sample. So it's kind of like those products are, you can be more or less sure that it's coming from the sample, but there is still can be something from the stage and other places. So now I set up here 0.3 milliliters per minute and click the apply button. And now I already did it before during Misha's talk to test if the cell is sealing. And you can see that you see the 28, which is the CO, C12 plus oxygen 16, 12 plus 16 is 28. And you have also double ionization, CO molecule be around 14, and 12, which comes from the carbon. So this are kind of like the products that are actually analyzed in the QMS. And I think I probably didn't close.
Maybe
I did already. The valve.
already closed
Okay.
here. However, I see the pressure. Yeah, pressure inside the cell.
It's
Here
coming
is the
down.
pressure inside the cell. It's increasing. Now it's 0.1 millibar.
You can go to probably 1 milliliter per minute or something to reach.
Maybe we can work in this flow mode.
Okay. Yes.
So I can open the pressure controller, so I increase the efficiency of pumping. And it is pumped to some pump. However, the gauge is here. So this is connected to some buffer chamber with turbo pump. So all gas which goes to the cell is pumped or to analyzer. There is a problem. We have burned the gauge for NAP lens for the first stage, so we don't know exactly the pressure. There is only Pirani gauge, which shows you just maximum -3, the minimum pressure -3. However, I think there should be like -6 now, because there is usually 5 orders difference between the pressure inside the cell and the pressure in the first pumping stage. Yeah. So
Well, normally we are changing those by ourselves. However, for this kind of operation, you need to evacuate, not evacuate, you need to open the analysis chamber or like let atmosphere go in. So it's not you need now, and we can actually, based on experience, even operate without this gauge, the vacuum gauge. So we just keep it for the time when we have time to change it.
So I started the X-ray source now. It will take maybe 2 minutes to start the X-ray source.
And to double check the pressure in the cell to be close to 1 minute.
Pressure in the cell is stable. And pressure in the analysis chamber, yeah, it's stable, so the cell is not leaking. Because sometimes we have problems that it leaks, and
all those things can just, if you put a color sample, some of them drops a little on the ceiling. It happened to us as well. So then it doesn't seal because the door,
yeah, which is
the ceiling around.
It's moving, opening and closing, and it's not always perfect.
Yeah, and the door cannot fit very well sometimes the proper position and all these things. So at the beginning, always should be very careful. So we start from the flow, which is the lowest possible. Check if the pressure in the analysis is okay. If it's okay, then okay, you can enter more gas and go further with the.
So we are close to 1 millibar, 0.98. It's let's say it's 1 millibar. If you want higher pressure, we just simply increase the flow rate here, but it probably will get there eventually. And when this, what we are showing now, so this here, so this is the NAP cell. You can see each of the chambers here behind us has its own vacuum gauge, a transfer, in situ load lock, the buffer chamber now. The buffer chamber is like -4 because we are pumping. We open the pressure controller and we are pumping the overpressure from the higher pressure cell through the buffer chamber. That's why there is a higher pressure. And if you go back to the measurement window, so you can see that this crystal is actually increasing the voltage runout and the power. And since it reached those values set up, so this was kind of green, and we will be able to measure. So
we can remove maybe the survey. I don't know if you need survey. Once we try to.
Depends here, 45 minutes.
I think it's not enough time to measure everything. I think it would be good to measure.
We have to measure definitely the carbon vision will be the most interesting because you'll be able
and
to
maybe
see
palladium it will also have maybe some oxidation.
Okay, so let's switch on the oxygen again.
I think oxygen is useless. Maybe 1 to 10.
Sure. Well, you can see there a little bit maybe the spectral field. So this will take around, let's say, less than 10 minutes. Plus to see, okay. You can do the whole measurement. How much is it? 5 minutes.
I'm not sure about this region.
So, you know,
maybe for me, we can also remove something and can increase a bit the scans for carbon 10.
Okay. So we can, okay, think now we are measuring the room temperature, so we can be sure the system is stable and there is no danger. However, if we heat up the sample, because of the thermal expansion, the stage is actually moving the sample forward towards the nozzle. So when we heat up the sample, we always have to double check the position. If you heat up to, for example, room temperature to 200 or 150, it would move the shadow or the sample closer, like let's say to this position. But if you go to higher temperatures, that would actually be quite dangerous. So on the other hand, if you stabilize the pressure and the temperature, the system is very reliable and it can keep those values for hours without any change. So we know that because we did some experiments. This one I showed you the first example published in Advanced Materials. It was the experiment where we are using the X-ray quite extensively. We know that for 8 hours, we didn't change the pressure or temperature since we set it up. So soon we'll be on the values. It's going to 40 watts. We'll be able to start the measurement.
So it is expected that signal maybe will be a bit lower than in vacuum because, as I told you, the gas attenuation usually at 1 millibar you lose maybe like 20–25% of signal, depends on the type of gas. With higher pressure, then it goes quite exponentially. 4 millibars, 5 millibars, it is already you have only maybe 10% of original signal. So then, and as I told you, it's quite a advertising trick how to have the specs advertise their machine. I remember when we were buying this, we were not very experienced, and they told us, okay, it's possible up to 20, up to 30 millibars, something like this. And but then later you realize that the things are like different, and yeah, you can feel the cell with pressure, which is 30 millibars, but to measure it, it's possible maybe on the single crystal, which is has very high intensive signal. So then, if even you have 10% of the signal, it's still possible to make more scans, and it's okay.
Yes.
However, as soon as you have some powder sample with 10% of some platinum catalyst, the original signal in vacuum is already quite low, and you need 1 hour to measure 5 seconds. But then, if you have 10 times smaller, it's just like useless. I mean, you might measure days, but nobody, of course, will do this. So yeah, you see now the difference. Actually, the shape did not change much, I would say, or maybe.
We didn't do the alignment again because we did already, and the sample didn't change its position. So you can see the signal is lower because you see the difference between the high vacuum measurement and the almost 1 millibar CO. So some of the electrons are scattered by the molecules, but it's not bad.
I think on the second stage we can try maybe to introduce also oxygen to CO. Try to make to see maybe some products. I think palladium at room temperature might also already catalyze something.
So here is the CO. This is CO signal 28. You see, if I fill it out, you can see in the beginning that when we introduce the CO, there might be, oh, this is actually from the previous one. No, start again.
So somehow water is increasing.
Looks like there was probably some rest of the water in the pipe, or it just stands for a longer time. So there might be some of those things. But the signal is actually -12. It's -13. It's quite negligible. This is our background. Sorry, not 13.
28. It would be 28. So this is -9. The signal from CO, and this water was -12. Yes, it's like 1 by -12.
switch back to this wave spectra, and after this we measure the oxygen. So I hope you are not sleeping yet.
No.
No. Oh.
No.
I think now it is not very well seen that the palladium spectrum is changed somehow. However, I think after we finish, we will export the data and open it in Colleagues PD and compare them together. I'm sure that will be seen that here is small shoulder. Of course, it's, I mean, with the XPS, it is quite difficult to see some changes which happen in two monolayers. Yeah, and in this case, the surface states, which should be somewhere here, of palladium becomes, I mean, to be occupied by CO, or these surface atoms are interacting with CO, and this peak from here, it switches to here, to the state which is a bit lower than bulk palladium. I mean, maybe higher, but not lower, higher, but then. So, and it is seen only when you overlap spectra, normalize them to same area, and then you see this small change.
Yeah, this doesn't allow us, but for SPD is quite easy to actually normalize and display those spectra all together. Okay. So you see this peak here. So it's actually the gas phase from the carbon monoxide because it contains carbon atom and oxygen atom. So the photoelectrons coming from this molecule is actually also measured. So you can see this is quite nicely seen. And this is the gas phase, and we'll see similar from the carbon. I'm going to show the.
I would like to find the presentation.
Which window do we show now? I forgot this time, the measurement.
So now you can see, yeah, if you look here, you see this gas phase, yeah, so small peak
Yes.
comes from the gas phase. And there is also some absorbed CO. However, as it overlaps with palladium, it is quite difficult to say, but I would say that I mean, after you again normalize it, maybe here will be some asymmetry. So somewhere here, I don't know.
The proper analysis by fitting to texture reveal it, and then you can subtract the platinum. Let's see. So here it is.
Yes.
Yeah,
We change the color. This is the gas phase. Now,
and 286 will be the.
and I mean, a big change, but I think it's here something. So this is some absorbed, maybe. This is maybe some carboniers.
But actually, honestly, it should be on. It should be on 26.
86. So maybe it was already occupied by CO from background somehow from the beginning. So it's why there is no. But however, there is this 87. Anyway, we should measure a bit more scans, then we might see. But anyway, I told you yesterday with aluminum alpha, it's usually very difficult to see some really changes coming from absorbates. This signal is so low that you should scan it I mean, so many times that takes hours.
Let's see, this is from the measurement. Okay. This is the clean one.
So here, just can you Brett stop the sharing, and I will share this and just to show you what I wanted. Okay.
You see.
No. I think you need to stop sharing.
Okay, stop sharing.
Yeah. So I would like to share you. Yeah. So this is some measurements which we've done with one our student on palladium. However, it was not NAPXPS. It was more like vacuum study. So the CO absorption was done in vacuum chamber and only one or two monolayers. I think it was 2 or 3 not monolayers, but long weaves. This was like kind of Ricci experiment. So you see here that the clean palladium, it is the black one, and after absorption of CO, you see very small changes which are not really seen very well on doublet. However, if you look on this part of the doublet, you see that at the beginning, if the surface is clean, it has here this small peak. So to fit this peak, you might fit it like here. So this is kind of two-phase palladium atoms. They are, as they don't have the neighbor above, so they have a bit different electronic structure. So their binding energy is a bit shifty. And however, I mean, this is only one monolayer. Its intensity of the signal from this one monolayer is quite low. So comparing to the total intensity which XPS is measuring, it's like several percent only. However, you see it, especially it's seen when you compare. And you see that when you do CO absorption, these surface states, they disappear and they like switch to here. And here you have this surface atom which are already poisoned or which are connected to CO. So there is a chemisorption of CO. And this CO was very well seen when we measured carbon 1s. So this is the clean palladium surface. This is the palladium after CO absorption. So it was CO absorption in evacuation. So short, exposure to CO. And then after heating, so we did flash to 600K, and all CO was removed. And you see again that the peak returned back of palladium. In case of oxygen, it was really difficult to see something as this palladium 3 peak is dominating, and it's so in that case we also did some UPS measurements. And UPS, as I said, it is much more sensitive to absorbates because there is energy with photons which is only 40 eV for helium-2, and for helium-1 it's only 21 eV. And you see here the spectra measured on clean and on CO absorbed. And here, for example, in case of helium-2 line, you see the bands which actually correspond to this CO, which is absorbed on the surface. So one is the bond which is between a kind of CO and oxygen. So this is the signal from, I guess, from oxygen. Another is from CO, from carbon and palladium somehow. And you see that the signal from palladium, this is the electrons which are on Fermi edge, they are decreased because of the process which is called electron back donation. So part of electrons from surface, they are, fill the empty orbital in the CO molecule. So this is the way how this chemisorption happens, and you see it quite well by UPS. So yeah. So here we go.
Just a question. So we can, in our proposal, we can include the UPS measurements.
We can do this because this UPS is developed for measuring in the cell as well, because there is a small window. However, it was installed last year. We tried it several times, and then window broke.
Oh.
Exchange the window, and then window broke again.
Don't worry. For your experiment, it will be installed already because we have the new one from Spec.
Yeah, then we discussed a lot. They tested. Then we found that they sent us back the window. It was already not transparent for helium-1 because they covered it with aluminum layer to make it stronger. Somehow this window was very weak. It was not because you have the source which has a long capillary, and you have the window which has the form of cone. At the end of this cone, there is a small window, and you approach with the capillary to this window. However, as you have there a discharge, so I think there is quite a lot of gas of helium and also some heat together with ultraviolet, which is heating this window, and they break after a short time.
So it's good that we have a new one.
Yeah, so we just recently received new one, which is covered by aluminum. However, it is not already useful for helium-1 measurement, but for helium-2 it works. The aluminum layer with thickness 100 nanometers is transparent for photons with energy 40 eV. So we would like to install it soon.
We are waiting for the good time actually when we can open the cell and
to vent the cell, to bake it, everything, because after opening the cell, we need to wait. I mean, I think in this shutdown, which we will have in the second half of the year, we will test everything and prepare. So at the moment, we can do only these experiments, which are UHV. So we can measure with the UV lamp in UHV. I mean, in the UHV manipulator without the cell. However, if you want to do the measurements in presence of gas, it will be possible maybe only after some time.
Okay.
Yeah, this is only what I wanted to show, what kind of change we can expect. So we saw at the beginning that we already had this carbon peak already on the clean palladium. So I think this CO came from some background, because really palladium 110 is very reactive, and whatever molecule of carbon would sit on it, it would stick there. So I mean, if you have pressure which is 10 in -7, it means that you, I mean, several minutes you need to create one monolayer of such absorbate. Okay, so this is everything.
now we have to discuss if we are just finishing, so we put the unit, or we try to heat it up to see.
So yeah, actually now we should decide. So I mean, this is how usually this experiment works. I mean, of course, this data, I mean, not very, they have not much sense, I guess. But anyway, it was just to show how to do this measurement. You see here, this is the gas phase. Normally you have some peak from adsorbate. However, on the clean surface, we already had some peak, so the change is not so big. However, I think if we try to add some oxygen and heat the sample, we would see how at some point we will see the gas phase from CO2. It would be somewhere here, I guess, a bit lower energy. So there will be this peak, the gas phase of CO will decrease, CO2 will increase. Also, you can see that at some point you would remove all this chemisoft CO, and there might appear another small peak which would respond to some adsorbed CO2 and some such chemistry you can see if you.
Let's do it. I will open the oxygen and just put oxygen in it a little bit.
Yeah, but then maybe we need to heat it, maybe a little bit too high. I don't know if it happens at room temperature. We can work another half an hour. We still have one
just sharply cut off 5:30 if no one more interested. However, we can just try to put the CO and try to do CO oxidation. You would see if we can some product room temperature. I'm not sure about that. However, we can simply start heating up the sample. Check out the position of the sample towards the nozzle and see what we can do, because we have the quadruple connected, so it may be kind of like it is an experiment without just not only one gas, right? Because it's more interesting in the combination. The oxidation makes.
However, the experiment usually works like this. First, you try each reactant by itself. So you try to see how your catalyst interacts with the gas, for example, with CO, then with the oxygen, and you test it at the temperatures which you are interested in, and then you try to make a mixture. So usually, if you plan some studies like this, so it's good to plan several experiments on one sample. One would be like a reference experiment with gases, then separately, then with mixture, and then so on. So this is the way how people usually write their proposals. They should put there the exact experimental plan, each step, so we can know what to expect.
We can actually decrease the pressure of CO to maybe half a millibar.
Yeah, and then put half a millibar of oxygen. Okay. So it is finished, I guess, in 50 seconds.
And we have the PC open, right? So it should be actually doable. So we don't need to open the bypass. Is it done? Okay, I will open the mechanical valve, and you can decrease the CO, and after that, just put the
Okay, so this is the last scan. So, I mean, we should be a bit quick, so we put not many scans. Usually, each measurement takes from 1 to 2 hours. I mean, to measure one group. So, especially spectra in which we are more or less interested in, we measure with like 50 or 30 scans and so on. It takes quite long time to measure everything. If you want to have, I mean, more or less like good data, not like very noisy spectra. As soon as you have noisy spectra, then it is a problematic to fit them because you don't know if this is here is the peak or this is only the noise, you know.
Yes.
Sometimes it happens. We have experiments where the active metal content is about 1%, and when you have a powder, press it in the mesh, you have it in 1 millibar of the reaction mixture. It's really difficult to see something. I mean, we did sometimes 160 scans, maybe for 3 hours, and it will finally didn't actually work out. So,
okay, so let's wait until the pressure in the cell will decrease to about 0.5 millibar. Then we will increase the flow of oxygen until the total pressure will be 1 millibar. So this is like such kind of rough way how to make a mixture 1-to-1 without any, I mean, calculations done. If you want to have it exactly. I just put 0.3. I guess we will need to increase maybe a bit, so like 0.45 maybe should be.
So we are changing a little bit dynamically the experiment plan, but this is experimental science. So we have also users come here, they have some plan to do, but we need to sometimes
the plan has to be changed during measurement, and it happens quite often.
This will be interesting to measure oxygen actually. So
okay, I guess it's more or less 50. So now we can try to add some oxygen to the pressure. And
at the same time, if you can display the quadruple and put it on the screen.
If I put it here, will it be visible? Yeah, so I can put it here. So you see that the pressure, also the signal from quadruple from CO decreased. At some point, we should start to see 32 signal.
So here, the little bump.
Yeah, it starts.
And 32 and 16 will be seen. Okay, it's coming. It's coming. We need to add more. It might be around, right? It's beginning to maybe more.
Depends. I mean, argon has mass like 40, CO has O2 has 32. So I think it depends on the atomic mass. Like which constant. But roughly, I guess 40. 32 and 40 is not so big difference.
Maybe a little bit. Let's see how this pyramid looks like. This is going CO and oxygen.
But so far, no CO2 at all.
True. 44.
The room temperature probably maybe some
a little. It might be just the background. We don't know if it was there before or not. Actually, you know, you can see.
Again, you can enlarge it here.
True. Or just pick out those 3 guys.
Remove it, yeah.
Okay, it's coming actually.
So you see the background was.
So even at room temperature, the CO oxidation on palladium already works because this was the moment where we introduced the oxygen in it. If you go back, display 32, you see exactly. This is the line from oxygen, and at the same time,
of course, the conversion is very low, but
CO2 starts going up. So it really works at room temperature. If you heat up the sample, it will be even more obvious. We are going there.
Maybe you can start heating. Then at some point we will stop measurement and we will increase
temperature dip. So in this case, again, we need to actually check the position. If the heating will be fast, but there is no time for manipulator to get warm much, so it will not extend too much. So maybe change. Okay, really small. So, and our measurement point is somewhere here in the middle, right? Okay, anyway, it doesn't matter. So, let's put this aside, and we can start. Where is it? So here we have another bookmark, which is the EDH, electron beam heater, and we are heating the chili. Yeah, I changed it because we have one cable for two manipulators, and we sometimes need to switch which manipulator we would like to heat. We are putting the current in the heater, in the filament, and it's start heating through the current coming through. And here we can actually observe the temperature of the sample and of the stage. So we're going up. Usually stage is hotter because, as I said, sample is heated by just being in contact with hot stage, and the stage is heated from behind, from rear side of the cell by just bombarding it by hot electrons. By higher electrons. However, there are other systems for heating. I think specs also sometimes use them. Is using some special ceramics, which have inside some resisting material or some like wires or so you can increase the current and you heat this ceramic. So in such case, maybe it is a bit better because you don't have a very hot stage. You can heat only locally small ceramics on which you have your sample holder with your sample. But in this design, it is a bit done in different ways. I mean, there are advantages and disadvantages. With such ceramics, you cannot go too high. I think the highest is 250 degrees C. And also, the speed of heating is much, I think, slower. You should increase the temperature very slowly because as soon as you increase it a bit faster, this ceramic is very easy to break. Because I worked once with such system, and it was really hard to increase the content. So more or less. Yeah, but actually, if you have CO plus O2, you have usually two CO molecules and one oxygen. So oxygen pressure could be not if you use the geometric pressure, you get the lower. But it's kind of like let's say oxygen rich. So you can be sure that every CO molecule is actually converted to. So I will read a little bit more. Which one is this? So even though we will probably not have time to analyze the data, we kind of tickle the fitting procedures. And of course, this is mainly based on experience. So the more spectra you fit, the more kind of like expert you are in it. And every system is a little bit different, and you need to somehow study the literature on that particular sample or material to also like compare already published data and get your own idea what you actually have. Actually, the idea is to measure spectra as we showed, and then of course to process them. And processing is as Brett said, just using such software like PolyXPD or CASA, just to find some peaks which are hidden inside this. In this measured spectrum, and then somehow to assign these peaks to different species which you have on the surface or bulk material. If it's, for example, oxygen is from some oxide and from some adsorbate and from different, I don't know, some water like contaminations and other carbonaceous contaminations. So this is like this. So I think
Okay, one question. So you showed in your talks that it's possible to measure the current. So in the electrochemical cell, you have some sample in the solution and so on. But for example, as I asked you, if you remember, we have a film in the FET configuration, field effect transistor, and we have 3 contacts. We have gate, source, and drain. And is it possible to do some kind of current measurement while absorbing the gas?
Yeah. As I told you, I mean, usually, I mean, this cell has no any like electrical connection or something. It was not designed in this way. So, and we had a lot of requests for such kind of experiments. So then we were thinking somehow, and we decided that we can try to work as I showed. So we use the sample holder. You just use these pins which you normally use for thermocouple measure temperature.
A thermocouple. Okay. So you use thermocouples. Okay.
Thermocouple pins and there's thermocouple wires, but usually I prefer not to use thermocouple the wires, but some kind of bolt which I connect to the pins, and then I mean these wires can be used for applying potential to your sample and of course for measuring current. But this will be only 2-point measurement. It's not like you make some 4-point like a normal sensor.
Okay, yes, we measure both 2 and 4, so mostly 2, so it's not a big problem if you can't measure 4.
We performed several such measurements, and for example, we had some sensors, and we were measuring really quite well the current. It was even we have here some potentiostat which was able to measure some nanometers, nanoamps.
Nanoamps, okay.
Yes, when we applied like 1 or 0.1 volts, because one user wanted to have 0.1 only volts, because he said otherwise he see very big shift of the spectra. Because as I told, there is a you apply potential, you always see this potential in your spectra. Your spectra are shifted by the potential which is on the place where you measure.
Yes.
And for example, if you measure on the surface and there is a drop of potential across the surface from one side to another, so it means it would result in broadening of the spectrum. Those different points on the surface, they would have a bit different potential. So electrons which are leaving from one side of measurement spot and another side, they could have a bit different kinetic energy, and then it results in some or asymmetry of your peak, or I mean broadening simply.
Yeah, that's right. Yeah, I can understand that.
Only 0.1 volt, then in such case you have a very small potential drop. But depends, of course, on material. If the 0.1 is enough to have some reasonable current.
Okay. And if we want to perform some test measurement, does that also have to go through CERIC application, or we can contact you directly and maybe try to squeeze in one day?
I think we can try also sometimes contact us directly. Of course, I mean, here it's quite difficult sometimes to find slot for measurements, but if measurements is not very long, it's not like you need 1 week of continuous measurement. Then of course you can contact us and we can try 1-2 days, no problem.
Okay.
It is I think not a big problem, because if you need a really long measurement, then it's better to try to apply for CERIC proposal.
Yes, I understand.
When you get exactly date, you get exactly time which you ask for support, everything. In case of collaboration, then it depends. I mean, depends on our time, depends on how much time you need for your measurement and so on.
Yeah, but you are right. It would be actually better to write in the proposal if you have some preliminary data. If it works, you retried it. It would actually like
sometimes even help for proposal to pass, because people which evaluate this proposal, if they see that you say, okay, in a preliminary measurement done in collaboration with us, then this evaluator, he sees that you are experienced, and usually we also can help you to improve the proposal. So technically it looks quite good. So then it increases the chance to pass
Yes.
evaluation. So,
Thank you.
some people do like this. They firstly contact us, then they try to get this proposal.
Okay, thank you.
So as you can see now, we are almost on 100 degrees C, and you can see that the sample position actually changed. It's a little bit. So if you go to higher temperature, it will be more crucial. So now it will also influence the spectra because you are in a different position. So you need to retract
the sample from the nozzle. Yeah. So I'm doing this using joystick.
Yeah. Okay. And now the question is, you can check how the spectrum looks like in the before.
You can check if we have more CO2. Maybe
Okay.
remove this.
Still about -12.
Yeah, but
Okay.
maybe you can remove this 28 and 52. So actually, temperature looks not changing much. Yeah.
But you know, when you go to high temperature, there will be another step. So you can still heat up a little bit more, just a little bit more, and
Yeah, but maybe you can
see.
start measurement just to see at least carbon 1s if it's different.
Okay, if you see something there.
Yeah, and then we can measure like at higher temperature.
Okay, so the group is prepared, right?
Yeah, just
It's
try
more
to
or less,
measure carbon 1s first.
it's still growing, however.
Maybe you can see the screen.
Yeah.
May I ask you guys, you are like PhD students or you are like master students or whatever? Because actually we were not informed what kind of students will be attending our practical session. So, can you say something? Because I think it's quite. I'm postdoc in chemistry. Okay. So, and do you have some experience with XPS, or why you did you decide to participate in this school and this NAPXPS? Okay, so you are quite experienced. If somebody of you are PhD students, somebody are postdocs.
Yeah, especially in chemistry. So because we are physicists, so you
Yeah,
might know
we are
more about
physicists. We
direction.
are physicists. We switch slowly to chemistry because
We are doing the chemistry, but doesn't mean we actually understand it.
yeah, so we are mathematics and physical faculty. Actually, our group is kind of physics oriented, but at the beginning we are like more like surface scientists. But recently, more and more we switch to this surface chemistry because first it is like I mean you have much more possibilities to publish. Usually journals are there are more journals in chemistry, and I mean citations, everything. So I mean to work in chemistry, it's I think much easier than in physics because real physics, pure physics, like solid state physics, it's quite complicated. The community is much lower than in chemistry. So I think.
Okay.
Okay.
So now you guys, you can actually apply for this equipment and through CERIC and come here. First time. Wow.
Okay.
We are quite experienced. Looks like to me. So you have actually, you can see here there are two different gas spaces, right?
I don't know if it's gas phase second. Maybe yes, maybe this is gas phase.
Because now we have the two gases. The inflammation of oxygen will be more.
At least this CO decreased. So, however, it looks like the absorbed states are still same. I mean, I would expect to appear also one more peak, which would be somehow related to some CO2 absorbed, you know, because I guess this is CO2 gas. This is CO gas. Yeah.
So, Andre, you are from Brazil. I was there 2 years ago visiting
Synchrotron,
yeah, there was this synchrotron build. It's quite impressive. And I also visited the center for like science. There was a lot of beautiful, nice microscopes. I don't remember HPS, but
was it which city was it? It was close to São Paulo.
yeah, it was in the São Paulo region and Soleil, so it's quite nice.
I've been at Soleil. Also, there was one conference like 5 years ago, and they had, I guess, excursion to Soleil, close to Paris, I remember. I was quite surprised by this wooden style, you know, synchrotron. I never seen it like this. Yeah, maybe it looks like actually. So maybe here something appears. Hard to say what is this. Maybe
It's a low binding
it's
energy.
quite low binding energy, but it looks like normal carbon, maybe 84.45. So maybe some kind of pure carbon is formed as soon as reaction, you know, starts. Okay, so we are informed that we have 5 minutes to finish this.
Yes,
So-
yes. Oh, sorry.
Yeah.
The Campinas, exactly. The Sirius synchrotron. That was actually very nice. I was very impressed. It was quite really good visit. It was Europe. It was from like European Union and just few people from a few countries to go there. So no one wanted to come from my side, from our side. So I was actually selected, and it was very nice. Yes, it is.
We were informed that we have 5 minutes to finish our practical session. So, okay, guys, if you have some questions, of course, I mean, it was kind of monologue from our side, and not many of you interacted with us, but of course,
We understand.
we understand. But of course, we thanks to
what we hope.
to Radmila, who communicated a lot with us. So if you have some questions, you can still ask it now because we will finish in 5 minutes.
Or just write, find the contacts.
So I guess we hope that you understand how it works here. So you put the sample, you do such measurements, you fill it with the cell with some gases, and you see some kind of such results that it's shown here. I mean, when you have some gas phase, you have some absorbate there. You see that changes are not really big sometimes, especially if it concerns the absorbate. But however, you can apply also for measurements at synchrotrons. Then you can decrease the probing depth by changing the photon energy. It brings some other problems like some absorption, stronger absorption by gas. So the signal is much more absorbed when you have like lower kinetic energy of this photo emission electrons. However, you can have much better signal from these chemistop layers, so the signal is not so noisy. But even with lab-based things, we can measure many things. So we saw examples.
As you can see now, it's actually visible. Even the production of CO2. We increase the temperature to 200 degrees C, and it already starts to really react. So the CO is consumed with together with oxygen, and you can see that the CO2 is actually it's produced coming up. So now we have on 200 degrees C a little bit retrace the sample to get it to the right position and it works. So Then you have, I think, different kind of samples can be measured here, from single crystals to powder. We can prepare here some samples in situ using operators that can be filled with palladium or platinum, wire cerium, whatever, gold, iron. This all can be prepared very well defined conditions, multi-vacuum. And well, we hope you enjoyed a little bit this session. We didn't bore you too much, and yeah, you had a good time.